Vou te dar um pro professor Ricardo e pro Samuel. Sim. Podemos já começar a falar. O professor vai fazer a apresentação?
Não, vai ser o professor Alessandro. Só te dar um. Tu dá o brief para ele.
O microfonezinho só para ter som online. Sempre deixa aqui pertinho.
Tranquilo.
E aí quando você apresenta, se você for fazer a apresentação de todos, aí você pode, se você aqui na frente, pode me entregar. Aí toda vez que você subir, eu te entrego. A gente desliga para preservar a bateria.
Sim.
O fechamento todo ligado. Aí já bota aqui para carregar.
Tá.
E
o meu, que eu, quando eu chamar, por exemplo, o professor Ricardo é o primeiro, eu passo o meu microfone e tu vai passar.
Eu vou dar esse aqui é pro professor.
Tá, esse aqui eu devolvo para a mesa para carregar.
Esse aí vai ser só seu.
Só para.
E esse aqui vai ser para
quem estiver falando. Perfeito. O passador tá lá?
Já tá aqui já.
Perfeito.
Professor?
Oi. Passa. Rodrigo, Alessandro, tem água ali embaixo? Tá cheio. Tem copo fechado, tem copo também. Danke. Vou ter que comer um filézão lá à noite. Onde? Lá em Coqueiros. A gente foi na reitoria, né? Vamos assinar o convênio. E aí já ficamos tomando trofi. Mas tava aqui um almoço, vai vir. Tá bem gostosinho. Aí eu gosto pra comer pizza, queria comer uma coisa mais leve. Não, cara, sei lá. Carne, né? Claro. Cada um que deixa aquele filamento, suei a noite inteira. E hoje onde que a gente vai? No Tangueiras, né? Eu vou revelar ainda na hora do almoço. Hello, good morning. My name is Alessandro. I'm from the Federal University of Amazonas, and I'm in charge for the beginning of this second day of our symposium to call the speakers. And remember that we will start. We have the two first speakers will be from the academy, and after the coffee break, you see some presentation from the private sector and power companies. We'll start with Professor Ricardo Ritter from the Federal University of Santa Catarina with the topic photovoltaics and solar second life batteries for green H2 production. Professor Ritter, it's one in my area, from specifically from electrical engineering. It's one of my reference related to the PV and energy transition. Please, Professor.
Thank you, Alessandro. Okay. So, thank you everybody for being here this morning. What I will do is I will try to entertain you, presenting what we do at the lab, but the real content will be given by one of our postdocs, Aline Kirsten. She will be talking to us from Germany. She has just arrived there for a 6-month period at the TH Köln under the Probral initiative. And Aline is leading our the scientific content of our hydrogen project regarding Second Life. So tomorrow morning is when Aline will give you more details. So I will walk you through our lab and give you some information on more general aspects of both photovoltaics, energy storage with second life batteries and hydrogen, how they all, and also mobility, how they all work together in our concept. And then in the afternoon, we will move to the lab and give you a tour of the lab. So I'll start with something that you have probably seen if you have listened to me before. So solar photovoltaics is not a new technology. It's been around for 70 years, but it's only recently that it has achieved the development level that we want for it to become an important contributor to the energy transition. So the first solar cell was only 6% efficient. This is 70 years ago. Now at the end it was small as a coin, okay, and very expensive. The payback of a cell at that time was 200 and something years. So we've evolved a lot, and these days module efficiencies, 3 square meter large modules, are 22 to 24% efficient, so much more efficient and much cheaper. The order of price development has come down 100 times from those early days. By the way, solar is as old as nuclear. And in the early 50s, nuclear energy came as a promise to have very cheap energy. So cheap that you wouldn't even want or bother to meter it and charge people because it would be so cheap. This, of course, as we know, didn't happen, mostly because nuclear energy requires so much care and environmental issues around it that in the end it is one of the most expensive energy generation technologies. So at the same time as the first solar cell appeared, the space race also was in place. The first satellites had just been launched, and this in 4 years after the first solar cell, the first satellite was launched with solar cells powering it. Before that, and this is how a satellite looked at in those days, very small with a primary battery, which would discharge over a couple of weeks. And after that time, the satellite would remain orbiting the planet, but dead. So the first solar cells were incorporated into this Vanguard 1 satellite, and it was launched with a secondary battery. And after that, it established solar photovoltaics as a very reliable technology, especially for space applications, but in those days still too expensive to be used in terrestrial applications. Now, if we want to talk about potential, and this is a slide that I've been using for the last 20 years, and the numbers have changed a lot in favor of photovoltaics. As you know, Itaipu is our largest hydropower plant. It's the second largest in the world. Three Gorges in China is a bit larger. It's a lot larger, much larger in terms of capacity, but in terms of hydrology, Itaipu generates every year more energy than the Three Gorges power plant in China. And it generates these days about 15% of our energy demand annually. The flooded area of the Itaipu Lake is 3 times as big as this island, 3 times bigger than Florianopolis. Now, if I want to cover all that area with a large, very large photovoltaic power plant, it would be 14 times as big in terms of installed power as Itaipu, 270 gigawatts. 270 gigawatts is more or less half of all the PV modules that were produced last year. So we would take half of the world production last year and cover Itaipu with that, and we would be able to generate more than 70% of all the electricity this country uses every year. So far from suggesting that, I'm just giving you an idea of potential, right? To know, for you to understand how big PV can be. But there are some very serious people, very important companies behind the concept of floating photovoltaics, in which they really want to put modules on floaters and cover flooded areas, lakes, reservoirs with photovoltaics. This concept started in countries that have very limited area availability, such as Japan, Singapore, and it really makes sense for them. Here in Brazil, for farms that have lakes for irrigation, and in which if you want to install large-scale PV, you would have to compete with arable, with food. It makes sense also to have floating PV, but not for the whole country at large, because in Brazil, these floaters here, which are typically made of plastic, UV-resistant plastic that has to stand 25 years at least, this costs more per square meter than land in the Northeast, where the large-scale PV power plants are being installed. But so that you understand why people are interested in this, even here in Brazil, is the scale. If we would install floating PV on all the areas that are used for hydropower plants in Brazil, the total installed capacity, if we would install them side by side, would be 8 terawatts, okay? And over 70 years, the cumulative capacity of photovoltaics in the whole world over 70 years has reached 1.7 terawatts. So this is why you understand how many companies, usually large companies, are interested in the concept of floating PV, because it's huge. So photovoltaics everywhere because it's become so cheap. Here, this is a solar plant in a hybrid wind solar plant in China. And all the white areas here this is snow. And as you see from the geography here, you will never have a city here. You will not have a university or a shopping mall here. So this is useless land except for this kind of application. And this other image also in China shows you that you don't even bother about changing the landscape anymore. You don't waste money making the land flat if it's not originally flat, just to accommodate PV, because PV has become so cheap. And here you see many of these modules are shaded when this picture was taken. And over the course of the day, you will have many of them shaded throughout the day. So PV everywhere because it's become so cheap. This is the largest PV power plant. It's in China, and it is 8.34 gigawatts, one power plant. The largest power plant in Brazil is 1.3 gigawatts, and it is one of the largest in the world, but this one here has 7 million PV modules installed over this 15,000 hectares, or 150,000 square kilometers. Another concept that is not new, it's from the 80s, but is now being more developed, is agri-photovoltaics, or agro-PV, or agrovoltaics, in which case you build the PV installation higher from the ground so that you can cultivate or have animals in the shade here and produce electricity at this level. And also because the structures are so high up from the ground, the modules perform better because they are cooled by the winds and the moving air around them. So for a number of years now, PV has been the fastest energy generation technology all over the planet. And here you see annual global net new deployment in gigawatts per year of new photovoltaics. And this is only utility scale, not rooftop solar, which I'll come to this point sometime soon. So over the last 7 years, PV has experienced a very strong growth. This is probably not new for you, but what is probably new for you is that it's been now for over 7 years growing faster than wind. In fact, over the last 7 years, and in the last year, this is So the green, the light green here is bigger than the sum of all the light green for all the other renewable and conventional energy technologies put together. So I've been showing this last year extensively, and most of the people don't know about this. But now comes the most recent data, and this is probably something that you have not seen yet. The red here is for last year. And I told you that the green here is bigger than the sum of the other greens. The red is now more than double the sum of the other ones. This is what happened last year. A bit further, 7 years ago, the installed cumulative power of photovoltaics has surpassed that of nuclear 7 years ago. Wind was surpassed in 2022. Last year, hydro. This year, natural gas, 25 coal. By the end of the decade, everything else combined will be smaller than photovoltaics. The reason for that is not only because it's beautiful, it's benign, it's sustainable. The main reason is this red orange curve here, which shows the price decline of photovoltaics over time. So it's competing with wind. Depending on the particular conditions, one or the other is the cheapest. But wind has to be large scale. So this is for wind turbines that are from 7 megawatts ups. And here for PV is as small as your roof, right? Your rooftop installation at home here in Brazil will cost only marginally more than a large-scale installation, because you have the roof, you have the electrical installation already there. You only need a very light and simple structure to accommodate the modules on a rooftop. So this compensates the lack of scale that you will have on a rooftop residential installation. So what is going on here in Brazil? So this is since the early days of the Brazilian legislation that allowed for rooftop PV power plants to be installed and connected to the grid, up to early this year, late last year. And the blue here, resolution is not that good, but I'll walk you through here. The blue is rooftop PV, and the yellow is large-scale PV. And you see that at the beginning, large-scale was bigger, but rooftop really took off when the news spread that installing a rooftop PV results in a much lower energy cost for the residential consumer. So this blue here is 70% of all the installed capacity in Brazil, and 30% is large scale. And here, the step from December last year to February this year is more than 2 gigawatts. So Brazil is presently installing more than 1 gigawatt per month. And then hydropower is now 48% of installed capacity, okay? This is installed power. This is not annual energy generation, because the capacity factors are different for the different energy generation technologies. So out of the 227,000 megawatts that we have installed, about half of that is hydro, and PV overtook wind and natural gas and biomass over the last couple of years, and is now the second and growing fast. So fast that we jumped 2 places. A year ago we were number 8, and now we are number 6. It will take us a while to overtake China and Germany. These guys here are installing about 5, 6, 7 gigawatts per year, and Brazil is now installing more than 1 gigawatt per month. So finally catching up, because ideally Sunbelt countries should be the ones installing and using more PV, because, well, they generate much more power per installed capacity. So this is our campus, and we are somewhere here now. So we have about 40,000 students, about 3,000 academic staff, another 3,000 supporting staff. So the population of Ufsky is about 10% of this island of Florianopolis. And we have installed on this building here, on the rooftop of this building, this picture here, we are sitting somewhere on the ground floor here. This is the oldest installation in this country. Still operating, you can visit it. It's going to celebrate 27 years of continuous operation later this year. In those days, it was not allowed. You are not allowed to connect to the grid. So this is the permit that the Celesc president in those days, in 1997, gave us to connect to the grid. Yeah, it was installed in late 27. We operated a bit in the black for a couple of months until we got this. So this is the Celesc president allowing us to feed energy to the grid. It's only 2 kilowatts, and this building uses much more than that. But let's imagine a sunny Sunday, and when everybody is at home and nothing is running here on this building, that you would be able to feed backwards energy to the grid. So this is why we needed this permit, because there was no legislation for that. It was only in 2012, so 14 years later, that you were allowed to do that. So 8 years ago, we got a big grant from the Brazilian Ministry of Science and Technology to build our new lab away from here, because this campus is very crowded. We wouldn't get area for a ground floor lab here. So we moved to the north of the island, and we will take you there this afternoon. So this is where we are now. This is the north tip of the island. This is the continent. And here is the Canasvieiras beach, very popular. And this is Sapiens Park. This used to be a farm, actually a prison farm, where the inmates had this semi-reclused sentence, and they would work on the farm during the day. And here at the Casarão, where is the Casarão? Here they would spend the night. This was closed for decades, and then the state government came up with Sapiens Park, and in an agreement with the university, allowed Ufsky to claim land to expand there. So we got this whole block here, 11,000 square meters, where we started with these two buildings here with the grant from the Ministry of Science and Technology. And all these other installations here are part of the ANEL, the electricity regulator R&D program, by which we got some grants. And more recently, we got this huge grant from the German government to build the new hydrogen and energy storage lab, which you will visit this afternoon. So with that came a problem, because I'm still lecturing here. Our students are still having their lectures here, and the lab is 26 kilometers away. So from the same Ministry of Science and Technology and Innovation, we got another grant to build this electric bus. So this is a bus that has batteries on top. It's pure electric, and it's been driving for over 120,000 kilometers. So this is 3 times around the world. 100% powered by solar photovoltaics. All the electricity that this bus uses is being produced on the rooftops of our building that you are going to see this afternoon. Now here is the bus, and these are the PV modules that are used to charge the bus. It's at the moment the largest load that we have. And the bus, after 120 kilometers, we are now replacing the batteries. And these batteries are going to be used in another project that Leonardo Pacheco from Celesc is going to give you more information this afternoon. We are going to use these batteries for a Second Life project and replace them with new batteries, and then the bus will come back to service. It used to do 5 trips from here to Sapiens every day. Actually, we would like to have ferried you to Sapiens with the bus, but the bus, you will see the bus, but the batteries are being removed here and they're being qualified for Second Life for this new project. So you'll see the bus, but unfortunately we will not be able to take you for a ride this time. So this new building here is an evolution from our original buildings in which you have the modules installed on top of the existing or of our roof. They are building applied photovoltaics, as we call them. And this was built 8 years ago. The new building, which was dedicated in August last year, is very new, uses the modules, which, by the way, are bifacial. So they take the reflection from the ground and from the surroundings as a boost. And also the walls are all PV modules, all bifacial. So this, close to 200 kilowatts, are used for the electrolysis project in which we produce green hydrogen. We also have here, and you will visit them, a container full of batteries, half of them first life, half of them second life, removed from cars that were used as taxis in São Paulo for 5 years before the batteries were removed. And we are producing hydrogen with solar energy, but all the electricity goes through these batteries. And I'll make a very important point here, which is basically what I came here to tell you this morning, that batteries will be needed for increasing the full load hours of hydrogen production. And the reason for that will be very clear very soon. So here we have these light poles here. We have been using Second Life batteries for 5 years now. We also have a small fridge for vaccines, for the COVID vaccines for the Amazon. We also have something else that I will show you in a second. But mostly here, we are trying to connect PV with storage, with mobility, and with hydrogen. So these 4 focus points are what is going on here. And for us, this building here, and this is something curious because I'm a professor at the civil engineering department, and we have to justify how PV works together with civil engineering. So PV is the skin. It's also the tiles. Oh, by the way, we are collecting rainwater. So what is it that you need to produce hydrogen? Water and electricity. 70% of the cost of producing green hydrogen is electricity. So you need huge amounts of electricity. So the building for us is also an equipment because we produce the hydrogen with rainwater and sunshine, and the equipment is housed here. And then we also produce ammonia. So you will see electrolyzers and a Haber-Bosch reactor working this afternoon. So after we produce ammonia, we react it with sulfuric acid and produce ammonia sulfate, which is a fertilizer. And here, this bit, which is still green, will house our new Agri-PV project later this year. So we'll produce the fertilizer to fertilize the Agri-PV project. By the way, Brazil imports 85% of all the fertilizer it uses, most of it coming from Russia and Ukraine. And we have the same problem as everybody else in the world these days. Another view of the lab. So again, PV has become so cheap that this picture is taken in noon probably. So these guys here have been seeing the sun all morning, but they will be in the shade for the rest of the day. The ones in the picture before, this picture is probably taken in the afternoon, yeah. So these modules are seeing the sunshine in the afternoon, but they've been in the shade the whole morning. So because PV has become so cheap, I can now afford to use it as a building element instead of marble, of polished stone and things like that. So for us, the building itself is an equipment because it hosts the electrolyzer and the Haber-Bosch reactor. It collects rainwater for the electrolysis, and it generates more than the energy that we need here. But it is intermittent energy, so we need storage. Now I want to make a point. This I kind of smuggled it into my presentation just to tease Alexandre Kupka, because now we're making the point of PV versus biofuels. He told us yesterday that ethanol should be regarded as a transition technology, and I want to stress that point. And it's a very long transition because ethanol program in Brazil has been around from the early 80s. So it's 40-something years old. And except for São Paulo and Mato Grosso, nobody else is using ethanol all over Brazil for economic reasons. For sustainability reasons, you might, but if you want to drive cheap, you are not using ethanol. So in 2008, this is our university theater, walking distance from here. It's got PV since 2004, PV here for the lighting, and PV here for a charging station. And this is a Fiat Panda that Itaipu lent us in 2008 because the Brazilian Solar Congress was held here. So we had this for a test drive in those days. But the idea here is that the footprint of a car is enough to give you the 1,000 kilometers per month that everybody on average in Brazil drives. So it goes like that. 1 hectare, so this should be a square. 100 by 100, 1 hectare, 10,000 square meters of sugarcane yields enough ethanol, first generation ethanol, enough ethanol for you to drive a compact car, not a flashy sports car, about 54,000 kilometers, which is just one turn on the planet. Now I'm covering the same hectare, the same 10,000 square meters with photovoltaics, and I'm getting the equivalent model of an electric car. And instead of this distance, I will be able to move that car a little bit more with the electricity produced on the same area that I was producing biofuels. In fact, it's not only a little bit more, it is much more. Much more. And as Alexandre likes to do energy balances, this is an exercise that we get our students to repeat this exercise. So the fine print here is the boundary conditions, and there are 2 main reasons for this to be true, and it is true, right? It's nearly unbelievable, but as you know, the electric motor is about 3 times as efficient as the internal combustion engine. Okay, mechanical engineering, everybody knows that. Electrical engineering, everybody knows that. Okay, factor of 3. Now, did you know that photovoltaics is more than 100 times more efficient than photosynthesis? So that gives you 100, and this gives you that difference. So, but what do we do with the batteries after they have fulfilled their mission in the car? Because when we still have a problem of range, electric vehicles, pure electric vehicles, battery electric vehicles don't have the range that the internal combustion engine car has, not yet. They might have with solid state batteries. People have been promising for a while now that you will be able to drive 1,000 kilometers on a charge and charge your car, your battery in 10 minutes, still to be brought to the public. But anyways, what will you do with the batteries after they have reached about 80% of their original capacity? Well, this is a Nissan Leaf car floor being dismantled in our lab. There are 48 modules inside. Each module has 4 pouches, so 2 in series and 2 couples in parallel. So the total voltage here in this configuration is over 300 volts. But what will we do with these batteries? So there's a lot of things going on here, and the Second Life topic is very hot, but it has a very important problem that Professor Schweiger mentioned yesterday, which is, so these batteries were manufactured in 2012. The chemistry today is not the same, and the cost and the price is not the same. And we have to compete with new batteries, which are probably 10 times cheaper today than they were 12 years ago. But so this is the challenge. We have to really come up with a solution in which the batteries have a value that is comparable or competitive with the first life, the brand new batteries. And maybe the solution for that is the environmental concerns, because right now, because the scale is still small, the automotive industry is not taking into account, like nuclear didn't take into account decades ago, what will happen with the spent batteries. If we just discard them, or if you want to recycle them, you are not taking or recovering the whole value of these batteries. So this is our latest project in the lab, and you will see these batteries here, second life batteries from a Nissan Leaf car, charging an EV. So, and this charger here, and this is the idea, it will never draw from the utility, from the grid, their whole capacity. So this is the big lung. This guy is, there is a solar carport here. So there are modules here feeding electricity to charge the batteries. At night, this is grid connected because the excess power here is being fed to the grid. In the evening or at night, we charge these batteries, but slowly with a very low power, 1 kilowatt, 2 kilowatts from the grid. But we never take the whole capacity of this charger from the grid. This is the inverter here taking care of that. So imagine now the fast chargers that are being offered in the market in Brazil today are ranging from 150 to 250 kilowatts. Now imagine you bought your electric car and you want to travel, and at a service station you get there and there is only one charging station, and there is somebody charging their vehicle there. I was promised that in 20 minutes I would be able to charge 80% of my battery of my car, but now on top of the 20 minutes, I go to the toilet and have a drink, and then in 10 minutes I'm ready to keep going. So 20 minutes is already a stretch. And if there is somebody there, I have to wait to use that station, not good. So there will be many charging stations, and if each one of them is 150 to 250 kilowatts, the infrastructure required to supply that power simultaneously will be huge. Will be much more expensive than the chargers themselves. So this is a very good solution for that, because the grid here can be a weak grid, doesn't matter. I will only need to charge the batteries very slowly in the night, during the night, from the grid. And during the day, I'll always rely on solar plus this lung here, which will be as big as needed. And ideally, it will use second life batteries, because these batteries will be made available in such huge quantities that we really need to do something with them before they go to recycling. And by the way, Second Life is buying time for the recycling business, which is not up and running yet because there are no volumes for that. So there are companies here in Brazil that are already investigating that, but they need volumes, and we don't have volumes yet. Second Life will buy you the volumes, will buy you the time. So finally, I move to green hydrogen. So green hydrogen, why green? It's transparent, it's colorless, it's odorless. You don't see hydrogen. It's the smallest molecule on Earth and the most abundant molecule on the universe. 70% of the universe is hydrogen. But here, because it's very reactive, you don't get hydrogen as a molecule available. There is a lot of talks about natural hydrogen, which is still a fairy tale at this stage. So green hydrogen is when you use a lot of electricity to break the water molecule and take hydrogen and oxygen out of it. So the main input is energy and water. So this is cost US dollars per kilogram. This is 808 natural gas. Natural gas with carbon sequestration and storage, which is another fairy tale. Coal and green hydrogen. Look, big range, ranging from 3 to 8, close to 8, maybe even more dollars per kilogram. So still very expensive. Nobody wants to buy them. We just heard this week that Unigel, the largest expected hydrogen project in Brazil, has been scrapped. More to come. So we will use hydrogen only when we cannot use electricity. And hydrogen was really a fashion, a fad in the early 2000s. Expensive and energy intensive. Energy costs were not where they are today. So with solar and wind becoming so cheap and environmental issues, hydrogen resurfaced a couple of years ago. So green hydrogen is only obtained through water electrolysis using some renewable energy as the energy source. Now, some people, some very important people, are saying that in 2050, and it's very easy to say something will happen in 2050. We will not be, I will not be there. Oh, I will be there. I hopefully will be there. Yeah, anyways, that Brazil will produce the cheapest green hydrogen on the planet. Okay, why is that? Because it has abundant and low-cost solar and wind energy, because it has a very organized and competitive energy market, and because we are reasonably close to Europe, the Northeast especially. So hopefully, high hopes. Actually, this is the last Intersolar South America in São Paulo, August last year. And there are people from this company here already saying that under some circumstances, which they don't disclose, you can already produce at these competitive prices. At this price here, I can sell green hydrogen, plenty of it. But we still have to get there. And how do we get there? So this is probably the most important take-home message I'm bringing you today. Here again, dollars per kilogram of hydrogen, green hydrogen, and the full load hours, the capacity factor, the utilization rate of my electrolyzer, okay? The year has 8,760 hours, and ideally I would operate my electrolyzer 24/7. And here on the left hand, I see I fixed the electricity price at $40 per megawatt hour, and I vary here the electrolyzer cost, capex, okay? And as soon as I reach here 3,000 to 4,000 operating hours per year, so if the full load hours are high, the capital cost of the electrolyzer plays a very small role if I operate many hours per day. Now I'm fixing the capex at this middle range here, $450 per kilowatt, which is still far from reality. And I vary here electricity price until zero cost. And you see here that no matter how much I operate my electrolyzer, electricity prices will dictate the cost of my green hydrogen. So this is very important, and this is why we need to optimize the electrolyzer operation. And the use of constraint off. So Brazil is sometimes not able to transmit all the solar and wind electricity that's being produced instantly, right? So we are constrained off. And there are people saying that you should use this to produce green hydrogen. How come? How can you justify? Because if you use this, you are operating towards this end of the curve. Doesn't make sense to me. Again, same curve, hydrogen cost, dollars per kilogram, and annual operating hours, the same thing, full load hours, right? So if you, and here different electrolyzer costs. €2 or $2 per kilogram is what fossil fueled base hydrogen is costing today. If you have solar alone in Spain or Portugal, you're around here. Onshore wind, it improves a little bit, If you do hybrid, you are getting there 4,000 and you need to get batteries to go there. And this is the whole point that we are going to investigate or put forward here in our cooperation. So that was the message I wanted to bring you. Thank you very much for your attention, and I'm open for questions. Thank you.
Thank you, Professor, for your speech. It's a very impressive infrastructure. Do you have questions? Gupta? No?
I was very clear. So there's no question because I was very clear.
Yeah. Just a moment.
So, Ricardo, tá me ouvindo? Dá de... So, just I'd like to remind that electric cars are as old as internal combustion cars.
True.
And so it's a question why electric cars have not been used, widespreadly still, and we still have resistance. I know technical limitations and such, but why do you think that is?
They're in fact older than ICU cars, but the range was, imagine battery technology 100 years ago. So the range was very short. And with Henry Ford and his cheap internal combustion engine cars, petrol started dominating. Also because in those days, the roads were starting to get built and people wanted to travel longer distances, not only commute inside the city. And the electric car didn't offer that range. An internal combustion engine is just make a big tank. So that was the original reason. So this developed and reached economies of scale that electric cars never had the chance to have. And now they are starting to have that chance for sustainability reasons. And that is the reason why it is probably going to be a game changer, a late one, but that is the reason why the internal combustion engine dominates.
But for sustainability purpose, ethanol is nearly as good. When you look into the whole cycle, not just, the charge electric car.
Yeah, but as you showed yesterday, you still have to harvest, plant, transport all the ethanol, and it's done with fossil fuels.
I understand, but that's the point. The point is that it's, I think it is unfair to look what is good in the other technology and what is not as good in the other technology, and that's part of the problem. I think, when you look into internal combustion engines, and even though you can talk about gasoline cars or ethanol powered cars, they have specific solutions that are very useful. So, for example, you actually mentioned, electric cars. Well, if you want to go to São Paulo, you might not get there.
Mm-hmm.
So it's, and I've mentioned that at the beginning of my presentation, there's not a single solution. It's
definitely
multitude of solutions. Therefore, we have to find what is the best solution for a certain application. And let's say if you want to drive, inside the city, you want to drive, 20, 30 miles every day, potentially, electric cars are a very good solution. I don't know if that's the range. I don't know if it's 100 or 200, I don't know.
Mm-hmm.
But for example, if you need to pull, heavy loads, electric cars haven't worked. That's been proven in the United States, for example. So my only point is that if you want to be fair, we have to couple the solution with actually the problem. There's not a single solution. I don't think electric cars is the single solution, at least with the technology we have today. So just, I don't want to, sort of monopolize here the discussion, but another point, you're talking about same comment goes to PV, right? You mentioned a lot about the cost, and the cost is dropping a lot. It's cheap. It's not a limitation anymore. And you mentioned about nuclear. Nuclear, it's slightly more expensive. But for example, when you talk about base power, PV can do base power. When you talk about the overall cycle, of CO2 footprint, nuclear pollutes less than PV.
Mm-hmm.
Overall. Actually, is 1/4 of PV, which pollutes, 10 times, 20 times less than a coal power plant. So it's about finding the niche, the actual solution where that technology can help us to get there. That's the only comment that I had. Thank you.
Yeah, you are right in terms of transition, but I would like to say that we will see a phase in, phase out. You will be phasing out biofuels while we are phasing in electric vehicles powered not only by batteries but also by hydrogen. Okay, so, and today there are developments in battery technology, sodium batteries, for example, very heavy, energy density is not as good, but for a car that doesn't leave this island, it is excellent. For you to drive to Sao Paulo, maybe the solid state battery, which is still a promise, will be the solution. As far as nuclear goes and the footprint, the PV module is very beautiful in terms of carbon footprint when it generates energy, but it has a very heavy carbon footprint because it's been produced in China, which relies mostly on coal. So when we have PV modules produced with solar-powered utilities, energy, then the footprint will be definitely lower than uranium mining, which is where your number is coming from. So you are comparing PV modules that are produced with coal electricity with nuclear. And this is where, if you want to be fair, you really have to take everything into account.
So last comment here, but other technologies can evolve as well. And as far as base load, PV, doesn't solve the problem.
No, PV and wind can never solve that, but batteries together and storage technology,
that's exactly
storage.
My point. We need a multitude of solutions. There's not a single solution. Otherwise, everybody would be doing electric cars. Mm-hmm. Everybody would be doing PV, and that's not the point. All right. So thank you. I'm done.
You are right, but this is why, even though PV will dominate, you will still. You see, this is not a stop to all the other technologies. It's just a dominance. Let's say that 80% will be PV. You still need the base load. You still need everything. And Brazil has the blessing of having Itaipu, which would not be able to be built these days because of environmental concerns. But for us, brings Brazil to the front stage of renewable energy and of sustainability. And it's not something that we would be able to do today. So I totally agree with you. We need a mix, but wind and solar will dominate because they are so much cheaper. And you are now going to the stage where you overbuild with PV. It's so cheap that you build more than you need. So we don't need in Brazil 1 gigawatt per month. Brazil has been growing about 3 to 4% per year in installed capacity. Out of 200 is about 8 gigawatts per year, right? The whole mix. And PV is giving you 1 per month. So overbuild with PV. Doesn't matter. It's so cheap. That's the whole point, right? But you're right. We are going to have a mix in which PV and wind will dominate.
Let's move to the next question, the final one, because you have a time schedule, please.
Ricardo, I have a question concerning floating PV. So it seems to be a very interesting option because the flooded area is already there. Why not use it for PV? But what's about environmental concerns? Are there any, like for fish population, for plants and so on?
You are changing the ecosystem. You are allowing less. So you have eutrophisation of the lakes. There is a benefit related to lower temperatures for the PV modules. There's a lot of people studying that, but in the end, the benefit is very small. And you have modules that will have to have a higher environmental enveloping because you get more moisture. So, and moisture is what kills a PV module. The warranty It's not because the solar cell gets tired of doing the photovoltaic effect. It is because you get moisture ingress, and then the cells degrade because of that.
But a part of the cell degradation, are there any discussions right now in Brazil whether to use these areas, or is it kind of a solved question? So because of the possible concerns for the environment, for the species in the water and so on?
For the large power plants, the thing kind of faded away, but for agricultural farms, in farms for their irrigation lakes, usually artificial lakes, it also helps with reducing evaporation, water evaporation, and it prevents you from competing with arable land. But it is more expensive than installing it on land, much more expensive. And you need the floaters, and you are working with 1,000, sometimes 1,500 volts DC level. If you open an arc at that level, it's very hard to extinguish it. So it's a safety concern too. So floating PV in Brazil, it's a niche. It will always be a niche.
Okay, thank you, Ricardo.
Thank you so much, Professor.
Thank you.
Let's move to the next presentation. That will be Mauricio Maldonado. He is professor and researcher from the Department of Production and Systems Engineering from Federal University of Santa Catarina, teaching undergraduate and graduate level courses. Yourself comfortable?
Okay. So, how much time do we have? How much time? 20 minutes? Okay. So, good morning, everyone. I will try to make my presentation as easy as possible so that everyone can join us at the coffee break later on. So I'm going to talk about second life batteries from a very different perspective that we've been seeing so far yesterday and in presentation of Professor Ricardo. And I'm going to show you an application in the UK, and then in a few slides later on, I will explain you why we chose the UK. So one of the big overviews that I want to point out first is that all of these recent events in terms of climate change, and we see energy transition going on, debates all over the world. And basically, one of the key elements that had been discussed as key levers for the energy transition and for climate change as a whole are technologies. And we've seen since yesterday how different technologies may achieve different outcomes. There is a whole bunch of different technologies. So for instance, we have in terms of electric power, we have wind, we have solar, we just talked about, we have hydro. We also have biofuels that was discussed yesterday. We can also look at energy efficiency, such as green buildings. We have EVs, electric vehicle cars. We have other rather more new technologies in terms of carbon sequestration, or even direct air capture that basically captures CO2 out from the air. And we also have rather promising technologies such as solar radiation modification, which basically injects aerosols in the atmosphere and creates a cover on the atmosphere. So the sun rays and radiation, at least part of them, reflect out. And so we have a lot of these technologies coming in. And the basic point that I want to show you first is, why do these technologies struggle? So there are many factors. Of course, it depends on these different technologies. We might look at costs. We might look at specific efficiencies or capacity factors, or even some political issues. So for instance, in this solar radiation modification, you're actually going to change the atmosphere, and you can change very rapidly the temperature on Earth. So in terms of politics, in terms of farming, what are the outcomes that these technologies could create? But we also have, as opposed to looking at specific social or political issues, we also look at other actors that are entering into this whole framework. So we look at, for instance, electricity providers coming into the transportation sector, in the electric vehicle domain, where decades or even years ago, they didn't have anything to do on that specific sector. We also might look into other infrastructure providers and so on. But I want to frame this whole discussion into some of the theories that we use in our group at the production engineering department, which is called the socio-technical transition. And this theory basically says that these changes, first, they take a long time in order for you to change from one paradigm, let's say one energy paradigm, one technology paradigm to the other. And these changes, they not only affect technology, they affect the social side as well. So how actors are involved, so how policies are made, so how the economy evolves over time. So we have changes in the structure of these systems, we have changes in the culture, where we can look at the social issues on the communities, on countries and so on, and we also have changes in practices. And we can look at these large socio-technical transitions. So for instance, when you look at a transition from a very traditional vehicle in the 19th century and even far back than that, towards the automobile that we know of today. It didn't have to take into account only the technological side or the cost side, but it had to do with changes in all of these three spheres. And so when we look at these big changes in these transitions, we look at some how these things happen over time. And this is one of the main theories that's behind this socio-technical transitions domain, which is called the multi-level perspective. And it basically says that in order for a technology to become mainstream on a specific arena, there are different levels that this technology has to get into. So the first one is what this theory calls the landscape, which are some sort of like the pressures, like the outer pressures that are creating some certain environment within this technology. We can call this, for instance, climate change. We can call it the regulations on specific countries. We can call it the promises for reducing emissions for each of these countries in terms of the UN. These are the landscape that defines these pressures, that defines this overall dynamics in this whole system. We also have the regime, which is this area in the middle, and the regime is conceptualized as the part of this multi-level theory where incumbent technologies are trying to get in. So we have established technologies here, and you have a market for those established technologies. You have users, you have science being held on, policy, culture. You have all of these aspects that are trying to establish and keep this established technology in equilibrium. So when we look at, for instance, the discussion between internal combustion engines and electric vehicles, we see that in the regime, you have internal combustion engines as the main regime, technological regime of this particular domain. And last but not least, we have radical innovations. So for instance, an EV, which has at the beginning of its time, it's sport in labs, in pilot projects, with very low efficiencies, but trying to understand this technology, trying to improve it, trying to make it better. And we have therefore many small arrows, because we have these different maybe types of EVs, different types of each of these EVs, like we said before, have yesterday, we have different battery types, We don't have a dominant or unique design of these batteries on cars, on efficiencies. And so we have all those small arrows that are trying to understand how this technology might improve. Then we have gradually these small arrows, they start becoming oriented towards the same direction. And they're trying to stabilize and create some sort of like in this theory, we call it a dominant design. So for instance, if we look at technologies like the internal combustion engine, the way you fuel your car is the same, regardless of the car manufacturer, regardless of the specific car model. All of them will work in the same way. And basically what this technology at this second moment they're trying to do is that they're trying to create similar designs, so at least in terms of a technology competition among them. Some of them will be faster, stronger, some of them will die out, so you have some sort of like evolutionary process a la Darwin, let's say, in a species, but in terms of technologies. Later on, we will have a new configuration. So now we have not just small arrows directed towards the same goal, but we now have one big arrow. So this technology is some sort of like converge into one new dominant design that is breaking out into this regime. So they are entering and actually they are competing against the established regime, which is basically what we've seen, for instance, in solar, what we've seen in wind, what we've seen in other technologies as well. And later on, once this happened, we have the last, during this time period, the last phase, the last stage, where you create a new socio-technical regime. So these technologies, the technologies that were established before, they will die out. Same rationale as a species competing over the fittest of which species the fittest, and then we'll have a new technology dominating this regime, which eventually even may lead to changes in the landscape. So when we talk about these renewable technologies, carbon sequestration technologies, and so forth, we're actually talking that at some point we want these technologies to change the landscape. So for instance, reduce carbon emissions, reduce the impacts of climate change, and so on. The thing is that in order to reach stage 4, we need a very long time. But one of the good things is that we know that most of technologies will behave in this some sort of like S-shaped curve that we call logistic growth. So we know that that's going to happen, but we don't know how it's going to happen, how long it's going to take, and how far are we going to get at each point in time, in a 5-year period, in a 10-year period, in a 100-year period, even though we know that this shape will remain. So the bottom line here is that each of these technologies are embedded in this larger system. So technology does not grow alone. So we look at solar photovoltaic or even green hydrogen or EVs. It's not just the technology or the efficiency that drives this growth in terms of market and so on, but there are other things that are involved embedded in what we call a technological innovation system, a TIS, which is one of the other tools that the theory of socio-technical transitions study. And basically this theory says that in order for a niche technology, this radical innovation to break up towards the regime, you need to have other things as, involved within this technology that may not be part of the technology itself. So for instance, you might have to create a market. So that's one of the functions of government, for instance, for this specific technology. You might have to give R&D, you might have to give funding, you might have to direct how legislation is being made. So you somehow drive this transition from this niche, from this lower level to the regime level. And so how we put this together in this specific case that I'm going to talk about, which is the EV batteries case for Second Life, and why we chose UK. At the time, one of our students was doing her master's thesis, and we had a colleague in the UK, Professor Peter West, which is an expert in EV technology in the UK. And the idea of this partnership, he had all of these things that I've mentioned before, like legislation, like all of these pressures, market pressures, environmental pressure, and so on. But he wanted to have some numbers, so we could, discuss more quantitatively how this particular use of Second Life batteries could work in the UK. So basically, this picture shows the life cycle of the battery. It comes from the car, and then you have some batteries that don't serve anymore. They will just go for recycling. But some of these batteries, they will be viable enough, at least for other applications. So that's what I've been discussing since yesterday. And throughout this some sort of like a checkup. And in fact, in the UK, they already have a system to check the health of these batteries. Then you can repurpose this battery and use it for instance, as a Second Life application as a battery storage system. So we use a simulation model to do that, and the specific methodology that we use is called system dynamics, which serves for problems where you have very long time frames. So like I mentioned in the previous picture, we have the logistic growth, but it may take decades. System dynamics is also well suited when you have feedback, material and information feedback. So if we look at the batteries and the recycling and the Second Life, all of these feedbacks into the system in terms of how much quantities of batteries, how much quantities of charge, and so forth I have. And the best scenario possible is when you can build this model out of some real data. That's how the UK helped us when we did this study. Brazil didn't have actually many EV cars on the road, and even less people were discussing about how we could use these batteries for Second Life. So that's why we took also the case of the UK. They had a longer time period selling EV cars. They had some sort of regulation already. They had some sort of even recycling facilities, a few at least, so that we could actually look into this case study in depth. So basically, the simulations models, like I said, they work when you have too long periods of time, very long delays in this transition. Either it's too costly to do a specific lab test, so let's say to look at this particular infrastructure and experiment with it directly, or either because it's too complex. So the first thing that we did, and I'm not going to have time to show this on this presentation, was to look at this whole technology innovation system of EV batteries in the UK using this framework that I showed you before. So these are 7 common functions that you looked at. So for instance, you have to look at market formation, how the market is building up for these Second Life batteries. You have to look at how resources are mobilized, basically from the private sector or from the government sector, so that you can actually have money to run these experiments, to run some other types of projects. Knowledge, how R&D is being developed, and knowledge and entrepreneurial activity, how many companies are being or startups are being created in this field, and so on. And you kind of connect everything in a more of like a qualitative analysis of this information. Then we model the flows. So this is a very simplified version of the model, but basically what it says here is that we have the cars that are running on the road, you have the batteries, then these batteries are collected because they end up their life within the car, and then they go to a recovery facility, and they go through this health inspection, of battery health inspection. If you have a good quality of these batteries, you can repurpose them and use them as, for instance, as battery storage units. If they are low quality, then you will go down here and then just recycle it and end of the cycle. So the first thing that we did with the model was to look at how the EV market will grow in the UK. And these graphs basically show the overall numbers till 2050. And we have different numbers for different vehicle brands at the time. And this gives us an idea of what's the total population of EV batteries that we will have for each period of time. So we have the first part of the model here. As you can see, it follows the logistic growth, the S-curve shape that I mentioned before. This comes inside the equations. Then we look at how many batteries we will have at each period of time. So in this business as usual scenario, which is the base case, the baseline scenario that we run, we estimated around 40 million EV batteries, which are ready for the health inspection and ready to go through maybe a second life, which is this second part here. Once they go inspection, we looked at some numbers. So about 80 million batteries by 2050 for second use, and about 20 million batteries for recycling in 2050 for you can do many things with this recycling. So for instance, there are some recent numbers that maybe around 80% of the battery you can take it off. And there are some startups in Finland, for instance, that are doing this. And you have, of course, many precious metals inside these batteries. You can use them for other purposes. You can even use these metals and these other materials to manufacture new EV batteries. In terms of extra capacity storage, by 2050, you would have something around 700 gigawatt hours. So just to give you guys a perspective, the UK last year they consumed 266 terawatt hours of the whole country of power. So this 750 gigawatt hour can be used in small storage, for instance, as in small solar rooftop residences and households, or you can use it also in large scale. It's a interesting number. So then we varied a little bit the numbers. We look at recycling. So what happens if we invest heavily in recycling technologies? We know now that it's very in its infant stage, and how we can actually recycle these batteries. Over time, these technologies and these know-hows will improve. And so we varied this rate of increasing this target, so that by 2050 we would have like 60% of batteries recycled. Beginning in a very low value, I guess it was like 1 or 2%, and at the beginning of the simulation, growing up steadily up to 65. We see now that we have more million batteries for recycling 24, little less batteries for second use. And the last scenario was actually varying both. So we keep our investments in improving the recycling rate so that we can get something like 40% of batteries recycled at the end of the simulation. And we increase also investments in second use batteries. So we could get around 12 million batteries by 2050, around the same number for recycling. And this, by the way, this is recycling at the first stage. These batteries, after their second life, they will also feed back into this big, some sort of like recycling stock. So actually these numbers could be bigger. Or even these batteries, after this second life, they can actually go and for third applications over the time. Oh, and the last number. So in this second scenario, as compared to the baseline, the capacity of these battery storage systems will reach a little over 1,000 gigawatt hour, 1 terawatt hour. Which still low if you look at how much energy is consumed in the UK, but regardless of that, it's still a considerable number in terms of reusing this technology, given some sort of like in a circular economy perspective, giving this technology a larger lifetime, and this lifespan could help us not only environmentally, but also, as I showed you, in terms of the electric grid of the UK. So that's basically what I wanted to show you. I hope I was clear enough. If I'm open to questions, thank you very much.
Thank you, Professor. Interesting numbers about EV batteries. Do you have questions? Yeah, Professor, a lot of questions.
Okay. Thanks a lot. So I have two questions. Maybe ask the first, then you, and then I ask the second one. Okay. Maybe it's very, very interesting to see your models, and maybe they can answer these two questions by some simulating. If you think for a very long-term perspective when everything is stable, so everything is a battery electric vehicle, everything market ramp down have been done, everything is a stable state, we have gone through second use cycle several times, stable condition. And in this case, what I'm wondering, if it's second life really saves resources, if you have good recycling processes. It would be interesting to know what's your opinion about this, or would it be possible to just find out the answer with your models?
So let me see if I understood correctly. So you're saying that if you have a good recycling procedures, then perhaps second life wouldn't matter?
Yes.
Well, it's still on debate. I guess the idea of this exercise was to show, at least to have some numbers of the volume that we will need in order to think about how can we process these huge amounts of batteries in the coming years. There are some parameters, and that's some of the key things here that define how the model will run. So these parameters are uncertain now. So for instance, we don't know today how much can we recycle the next year. So these estimates more so help us only to have an idea of how much this whole market may grow in a long term, so that we can actually prepare now, investing in R&D, investing in creating market formation, investing in creating startups, so that we can actually have, once we get there, an ecosystem that it's at least fully prepared to manage these huge amounts of EVs. So I'm not sure if I answered your question.
Yes, because I think as this recycling process or flows of this similar like a chemist, and I'm a chemist, does, if you have a reactor where you pump in some liquid, reacts, and something else comes out. So that's what I try to understand it like this. And if you have a second life concept based on this reactor model, you just have a pipe, straight pipe, or one pipe with a loop. And at the end you pump in, just goes the loop, it delays a little bit, but it's the same what you pump in the first side comes out on the output. So that would be interesting to investigate from a long-term perspective, if it's better to have second life maybe, or it's better to skip it. Yeah. So that's what I want to understand. And maybe we should discuss it later on, how to make such model doing also this analysis.
Yes.
Okay.
Thank you.
Thank you.
Yeah, and I think these modules will have to take into account what are the expected values of the metals that you get back from the recycling, and the service that a second life product can give you. Because dismantling a battery for second life is a big hassle, and it's a big cost. And it's still a big question if it really will, if there will be a second life market when volumes are big enough. But my question is regarding the recycling. In your studies, have you come across any Brazilian company interested or starting to doing that?
Batteries?
No, Brazilian company
in Brazil?
In doing recycling or studying recycling.
Well, not in batteries specifically, but in solar. There is this company.
Yeah, there's Sonar. Yeah, but for batteries, because the second life of the recycling model for modules is low tech, very low tech, and low volumes are already okay. But you know the company Fundição Tupi, foundry, they do engine, ICE, and probably a BMW in Germany is probably using a motor block cast here in Brazil. So they're huge. They are operating in many countries, and they are here in Joinville, our neighbor, Fundição Tupi with a Y. So these guys are already looking into, and they're just waiting for the volumes to be there. And before that, they're even considering that if they should not go into the second life market, so sourcing the batteries, putting them together as second life products, and so that they know where the batteries are, leasing them out, and then they know exactly the day when they will be ready for recycling.
Right.
So maybe you should look at this company because they're really getting there, because they know that they will be dead in a number of years doing as a foundry for ICU engines. So they are looking for their survival. And also because they understand the hydrometallurgical processes involved in recycling scrap iron and steel. They have the know-how. Yeah, they have the basic knowledge, and they're big enough to be able to afford the investments for the volumes.
Great.
So there are people getting prepared for that. It's still medium term, but it's where they are heading.
Thank you. Yeah, we'll look into what Tupi is doing. Thank you.
Thank you, Mauricio. Very nice presentation. Just general question. I'd like to take your, what do you think about, generally, human beings are, averse to change. We don't like to change. We like things the way we do. And so when you think about transitions like that, and especially talk about energy, not just about transportation in general, any, sort of energy that we have to deal with. How to deal with this potential necessity for the change of behavior that we have to go through. And I know I can give an example. It seems like a dumb example, but when I was a kid, we had seat belts in the car, but nobody would wear the seat belts. And then a regulation came about and said, now you have to wear the seat belt. It was a big change, So the next generation, so my son never sat in a car, without wearing a seatbelt. So there was a change in behavior that we went through. So is that necessary for energy? How do you see that happening? What's your take on it? Thank you.
Yes, thank you. And it's a crucial necessity. That's why when we look at these technologies embedded within a larger system, at least with this very interesting concept that I showed before. You don't have the risk of surpassing some important things that are needed in order for this technology to come up. So when we look at, for instance, these landscape pressures, they can be as big as climate change or as small as a regulation in the UK that bans the use of landfills for car batteries. So in terms of small time periods, you won't see huge changes in user preferences. You won't see much changes in user behavior. But as you said, these pressures keep coming in all the time. Towards a longer period of time, you'll see how these pressures start changing. Even the behavior of the user, when the user might, in a 5 to 10 year period, this user will have enough time to think through and say, oh, I'd rather buy an electric vehicle because gasoline prices keep coming up and up. So it takes a long time. And the idea of these theories that are behind these socio-technical transitions lens is somehow to look at these other intangible aspects that aren't really concerned. People usually is not concerned about or are even really aware of these other factors that are embedded within this particular technology. Thank you.
Thank you so much, Mauricio. We will stop now because of the time. If anybody has some further questions, you can do at the coffee break now. So you have 15 minutes as coffee break, and you come back 10:45. Okay, thank you so much. Welcome, Leonardo. The presenters here.
Okay.
Make yourself comfortable.
Okay, good morning, everyone. First, I'd like to say thank you for the invitation, for being here. It's an honor to present alongside with so many relevant research in our area. So I'm going to present the R&D project that I'm currently developing with the CELESC and the university team that has a rather long title. It's Multifunctional Transportable Energy Storage System via first and second life batteries to support shutdowns and attend seasonal demand peaks in the distribution grid. So this is the resume title. And I work at the CELESC Distribution. This is the power distribution company here in Santa Catarina. And I'm the project manager of this project we are developing. Okay, sorry. Não foi. Technical problems. Okay, thank you. So we have some main information. So our deadline is 24 months. We start the 1st of November of last year, and we have 24 months to complete this project. So we have the CELESC team that composed by me, the project manager, and 5 other members of the company who was working with me in this project. We also have a support team from our company. They are composed by members of the R&D division, so they help with some things other than technical. And we have also the university team. They are led by Professor Elena, and they are developing this project, this prototype, so we can apply it on the distribution grid. So we have a global objective, and we are aiming to bring a series of contributions in the context of using energy storage technology. So we are looking for learn about first and second life, about the application of batteries in the distribution grid. This is our first objective. And we're going to do that with the installation and operation of a multifunctional transportable energy and storage system. And we're going to use lithium-ion batteries. Here in Brazil, we have a Portuguese acronym that is STIB. So we're going to integrate the system of batteries into a semi-trailer, and we're going to have first and second life batteries. And we're also going to have a diesel generator with a backup function and STIB range extender. So if the batteries run low, we can still have a diesel generator to don't turn off the consumers that are connected to this system. And we're going to connect it to the low voltage distribution grid in the voltage of 220 volts, or we can also connect to the medium voltage distribution grid. Here in Florianopolis is 13.8 kilovolts, but some other parts of the state it can be 23 kilovolts also. And we're going to connect to the medium voltage distribution grid through a dry type or hybrid transformer. So we have a team who's going to install the dry type, but we also have a second team that is working on a hybrid transformer, so we can use as an alternative. And we have 3 main goals that I'm going to show to you after. There is support shutdowns, that we have scheduled or emergency shutdowns in the distribution grid, and also provide energy during seasonal demand peaks. I don't know how many of you are from here, but in the summer, we have a demand higher than the rest of the year because of the tourists. And we also gonna control reactive power flow in the distribution grid, also connected to the medium voltage grid. So this global objective can be divided in some specific objectives. I'm not gonna read them all to you, but I highlighted the most important parts of each one. First, you're gonna study storage technology. So this part is almost covered because we have a very good team working with knowledge of this topic. Then we're going to evaluate via computer simulations the impact in the grid when we insert this system. This is something new. This is not very common. We have a storage system. I believe in some years we're going to have a lot more, and it's going to be a concern for the power company too. But we have to run some computer simulations to see what's the impact of inserting the STIB into the grid. Then we're gonna test the 300 kilowatt hour first life energy storage system. So we're gonna have 300 kilowatt hour of first life battery and 100 kilowatt hour of second life battery. So we have this difference. So first we're gonna test the 300 kilowatt hours first life batteries. Then we're gonna acquire and characterize second life batteries. Why do we need to characterize? We need to learn. We need to know how is the state of health of this battery. Professor Ricardo said before that we're going to use the batteries from the electric bus. So we need to study, we need to see how much charge can it hold, how much time it can provide energy. Then we're going to acquire the semi-trailer system, all the batteries, the power converter system, and all the transformers and all the parts is going to be on top of a semi-trailer system we're gonna be able to carry around in the city. Then we're gonna perform the integration, storage, and supervision of second life energy storage systems in a controlled environment. So we're gonna exclude any unforeseen problems in work done first in the controlled environment. Then we're gonna parallel with all this work, we're gonna develop a hybrid electronic transformer with other team that is already working on it, so we can change the dry type transformer for electronic transformer, who's going to be a lot of features that can help our implementation. So we're going to assemble and test the STIB completely. Then we're going to install the system in the laboratory of the university that we are going to meet this afternoon. And then we're going to install the system in the connected points defined in the first objective. So we already choose a point in the grid. Then we're going to connect the system in this point so we can test it on the grid. The point was chosen near to the laboratory, so the research can be closer to it and study and don't have any problems with that. And next objective is to operate and propose and install STIB. So we're gonna operate it and we're gonna acquire operational data. So we're gonna see how it works, how much time, what's the temperature, what's its performance, efficiency, and then we're gonna perform an optimization. Okay, we know it works, we know its efficiency. What can we do to make it better? What can we do to perform better, to recharge or discharge better? Then after all of that, we're going to prepare technical reports and instruct the Celesc team, because after the project is done, the Celesc will still have the prototype. It's in our interest to continue to use it on the grid. And then prepare final reports on the conclusion of the project. So this is a block diagram view. So we have the second life, first life batteries connected to a power converter system. And then with the diesel generator connected to a energy management system, we can connect it to the grid with low voltage or medium voltage through a dry type transformer. This is a view or expected design that was created by our team at the university. So we have the same things, but we have an approximate view of what we expect at the end of the project. So it has the first life, second life, the inverter, dry type transformer, and other parts of the project. Here are some other views in the semi-trailer completely. So we have three main applications. So we developed a strategy to apply this system. So the first application will be to achieve peak shaving. So what we're going to do, we're going to connect the prototype to the energized low or medium voltage. We're going to choose low or medium voltage and connect it. And we're going to reduce the current supply from the feeder. So our company has a lot of feeders that goes in the city and provide energy to the consumers. So we're going to connect the STIB at the system, at the grid, and we're going to provide energy so we can reduce the current supplied from the feeder. This is going to help at some moments of high demand peak and perform the peak shaving. The image down there show us what's peak shaving. In the moments of high demand, we're gonna discharge the battery. So we're gonna bring this peak a little down, and at the moments of low demand, we're going to recharge the batteries. So what's the advantage for this first application? So the grid will determine the voltage. So we have infinity bus. We don't have to worry about frequency, voltage levels, or balance of the phases. The grid is going to do all that. So the inverter will read the grid, the voltage, and inject the current in phase. There is no need to create a grid. There is no need to turn off consumers. This is an important feature of this system. Our company doesn't want to turn off consumers. We need them to be energized all the times. So the first application, we won't be turning off any consumers. So we have the possibility to control the battery power flow. So right now I want to see the behavior of the prototype with just 50 kilowatts, with just 100 kilowatts. We can control this. And by controlling, we can analyze the prototype behavior for hours. And there is a free choice of connection points. Every place in the city, there is a electric grid, so you can connect everywhere. But like I say, we choose a point close to the laboratory. What's the drawbacks of this first application? The time we're going to take some time to safe operation and the validation of the operational procedure. This is something of the company. Every time we're going to do something on the grid, we have to perform a procedure. Each step has to be performed perfectly, so our workers can work with safety and we don't have any accidents. So since it's gonna be the first application, we're gonna take some time to learn how to connect the system, how to turn it on, what to expect when you turn it on. And the lacks of experience, so we're gonna be in the first application, so we're gonna have some unforeseen problems we don't know yet, but I believe this is gonna be a problem at the first application, but then we're gonna learn, and this won't be a problem for the next applications. We're gonna have to work in live line, so this is our way of working, and where our workers they work at the grid with the grid energized. So this has to be a specific procedures, so they won't get hurt. It's very dangerous. We need to do very calmly. Since we're gonna work with live line work, there is a possibility to cancel the application at that moment due to other conditions. So we don't work, for example, when it's raining. It's a problem with the voltage, and it's not safe for our workers. And since it's going to be one of the first applications, maybe some failure can open a fuse switch or have a problem that may disconnect some section and some consumers. So the second application, we're going to do almost the same thing, but now we're going to inject the currents off phase. So in this manner, we can control the reactive power flow. So our feeders have active power. They provide active power and reactive power. Since we have a lot of motors and other devices connected to the grid, we have to provide these two types of power. So it's interesting for the feeder to have the lowest reactive power flow as possible, because we can also control the voltage level of the grid. If you have a lot of reactive power, we have lower voltages. So the advantage is almost the same. Well, there is no need to turn off consumers. We can control the battery flow, can watch its behavior. The drawbacks are almost the same too. Live line work, we have cancellation due to weather conditions and possible failure, and some new technical difficulties due to reactive power injection. So there are some things we have to analyze when injecting current off phase, and may create some problems, but nothing we can deal with. And the third application, I believe, is going to be the cause most impact. It's connect the prototype in a section of the low or medium voltage grid that will be disconnected to supply consumers during a shutdown. So in a company, we have a lot of scheduled shutdown. So sometimes we need to fix a pole or change a cable, and we need to turn off the consumers. And this project will help with that. Some consumers can be saved from the shutdown and can still have energy while we are performing our work. So the advantage, at this point, I believe we're going to have a lot of experience with the prototype. We're going to know how to turn it on, what's the possible problems, what can we do about it. We will have the possibility to use the range extender. So if the battery runs low, we can turn on the range extender and see how it works, the diesel generator. And some customers, but not all of them, will not be turned off. So what's the drawbacks? Now we have an isolated grid. So our prototype will have to create its own grid. So we have to be concerned about frequency, voltage levels, phase balance, and other things that we have to be concerned about. There is no load control, so we can control when the customer gonna turn on a motor or a welding station or something like that. So we don't have control of this load. Transporting the prototype to the point of the grid, it will be connected. Maybe some point is difficult to a truck like that to get there, so it's gonna be some trouble with that. The risk of short circuits in a consumer. So a consumer can have a faulty device that can cause a short circuit. Our prototype has to be ready to deal with short circuits. And the transition between the energized and off-grid may cause unforeseen events. So the moment when you open the grid, our prototype will have to make this change as quick as possible so the consumer won't feel it. So let me bring you closer to what we do every day in a company. So we have an example here of a scheduled shutdown without the STAB. So imagine that we need to change the cable or the pole, or we have a service to do in that section. It doesn't matter the service, we have to turn the section off. What can we do? So we open the fuse switch. When we open the fuse switch, all the section before it is gonna be shut down. And no one in the section will have energy. So there will be turned off here also. But the service, the job we have to do is only there. Why these consumers will be without energy too. But if we have a STAB, what can we do? So we have this section here, the same work. We have to do something that is gonna have to shut down this section. But what can we do with the STAB without the two transformers not knowing? The other transformers, there is nothing we can do about it. He's gonna be turned off because the service is over there. But what can we do to save these other two transformers and all these consumers with it? So first, we're gonna connect the STAB and turn it on. So he's gonna deliver power in parallel with the grid. Then we're gonna open the switch, and at this moment, the STAB is gonna provide energy for the two transformers alone. He won't be the backup of the grid. He's gonna be he has to create his own grid and to provide energy to the other two transformers. Then we're gonna open the other fuse switch, and now the section we need to work is isolated. Our workers can work at this place with safety. So we have a section turning off, and we have another section energized. I believe this is gonna be the main contribution of this project, because I'm talking about a scheduled shutdown, but we have emergency shutdowns due to the rain or any other weather conditions that can happen. A lot of times we get an important place that goes out of energy, like a hospital or a clinic. So our prototype can go there and provide energy to this place. At the same moment, we are fixing the grid so it can go back on. So this is some important features. We are producing knowledge, so we are producing studies, papers, and reports. We have students in graduation, master's, or doctor's degree level. Quality energy. We are making improvements to the power flow distribution by performing the peak shaving. We are controlling the reactive power flow, so we are controlling also the voltage levels too. A non-stop power supply means an undisturbed consumer. This is very good for the image of the company. So anyone don't have any shutdown whatsoever. And the possibility to provide energy in emergency situations. So this is very common. Whenever we have a rain, we have problems and we can help with that. The semi-trailer is movable, so we can provide energy anywhere within the states. And we have also a new use for second life batteries. as we are all seeing in the other presentations, we can use the second life batteries through this application. The reuse of batteries that could be discarded, as our other presenter said. And we also providing a sustainable technology. So thank you for your attention. I'm ready for questions.
Congratulations, Leonardo. Do you have questions? Any questions? Yeah, one.
Thank you for the presentation. I don't know if it is. Can you hear me? Or
I can
is
hear
it
you.
kind of low? The question that I had is more like economical. If you have this number, just a curiosity, because of course there are things that are intangible in terms of the image of the company, which is different to measure, but there are other things that are more able to be calculated. For example, the solutions that you provide increase the quality of the delivery of energy with is indirectly measured as a measurement for the Celeste, for example, to renovate its concession or to increase the value of the energy that they sell. So my curiosity is how will be the payback of the system like this? Like how much better the company can see the energy if implement this kind of solution?
Okay, good question. The payback will depend on the shutdown. This is example, we have a low payback. There are 2 transformers only, few consumers. So it's not a very high payback. But the most important thing is our quality indicators. So we have to, the company is more concerned about that than the money we're gonna continue receiving or something like that. So the money payback is gonna be depending on how much we use it. If we see a system that we can use it every day, we have a payback faster. But I don't have a number to tell you. But the most important thing we are concerned about is our quality indications. The duration of the shutdowns and the frequency of the shutdowns has to be as minimal as possible.
But you're also penalized by that.
Yes.
By the regulator.
Yes.
I guess that because of the time, you have to move. Leonardo,
Okay,
thank you so much. If you have any questions, you have the contact of Leonardo on the last slide. Thank you, Leonardo. So the next presenter will be Vitor Gola from Micropower with a case study. Thank you. Thank you, Vitor. Presenter here.
Valeu, Gustavo. Hello, everyone. It's really nice to be back. Thanks to Professor Ricardo for the invitation. And today I would like to talk to you about the first energy storage VPP, a virtual power plant, the Micropower, the company that I work for, is developing here in Brazil. First of all, my name is Vitor. I'm an electrical engineer and graduated here from the university and a former researcher at the photovoltaic UFSC laboratory. As you can see, my bachelor thesis was related to the second life storage that Ricardo has currently installed in the laboratory that you guys can visit maybe today or tomorrow. And I work as a project engineer, focused mainly on grid solutions at Micropower. I'd like to show to you, start the presentation, showing maybe the image is not that good, but you can see here in blue, it's the renewable energy in the grid in a typical Sunday here in Brazil, just summing the wind and solar resources. And in the orange line, you can see the hydropower that is being developed during the day. You can see, maybe can I point here? Here. You can see that during the sunny hours, mainly from here 9 to 15, we have this huge curve that inverts the power that is being developed by the hydro plant. When the loads, the sun comes down and the loads go up after the 6 p.m., you can see that it's really hard for the hydro plants to provide all this power needed during this specific time. This information is even better presented here, that you can see that the sun is phasing out, and the load, the sun of everything here, is really high in this peak here. The same information is presented here, and you can see that this ramp is about 28 gigawatt in just 3 hours. This means twice the power of Itaipu. You can imagine the huge impact that these power dynamics have in the grid. Of course, this is something that the system operator can predict, but sometimes we have huge events, for example, the World Cup or the Olympics, or even elections, that are kind of tricky to predict since they are out of the typical days that we have. This is the case that we're studying a small distribution company here in South Brazil. They have almost the same problem, but of course in a smaller scale. That you can see they have, during the solar hours here, this curve that you can imagine as the opposite of their solar generation. That's why they have a huge penetration of distributed generation here, and it's hard for them to deal with this during the day and have the flat curve, the really high power demanded on the other part of the day. If we take another day of the same distribution company, this is a day where the loads are much lower. You can see here we have something around 1020, and here we have something around 400. So in this day, as we have really low load and really high generation, in the peak hours here of the solar, we have the inversion of this power grid. It's stopped from being a load for the distribution company that feeds energy to them, and they starting to be in generation unit. So this is a problem that not only these distribution companies have, but you can see the cases of CPFL, CEMIG, Coelba, huge distribution companies here in Brazil that do to the solar generation are having this, we call it flux inversion, where we are the loads stopping being load and they start being power sources. This is really hard for the distribution companies to deal, especially since the protection infrastructure, the transformers, everything was designed before this problem came, and here we have a huge problem to solve. Again, if I put both curves, you can here see the huge influence of the solar generation at the same times of the day in 2 different days. So why should we use batteries for solving this problem? First, batteries are really flexible. We can operate in the 4 quadrants of the power diagram here, so we can deliver or consume real or reactive power, and this is really valuable since we can operate as loads, as sources, or even trading the reactive energy for other possible applications. Batteries are really fast because the instant power ramps are amazing in those situations that I show you, the 3-hour ramp that we needed to solve in the Brazilian grid system. It's really hard when you have power generation for coal, as an example, because they need much slower power ramps that could be solved by batteries. Batteries are really smart, and this adaptive and autonomous operation can help a lot with different applications in solving this kind of problem. And of course, the sustainability, since no greenhouse gas are emitting during the operation, especially in Brazil, because we have a really clean energy matrix. Of course, they have some carbon footprint when we go for the production and this kind of thing, but much lower than coal, for example. If we bring back the same graph as before, this is an example of a 4-hour battery operation that could help in this case. We could charge the batteries with this excess of solar generation here, so we could drop this curve down and make the the hydro plants much more flat and predictable. And we could discharge the batteries here in the peak time, so we could lower this need of the hydro plants here, so the system would run much more flat and more smoothly. This is an example of one project that we have operating, a facility of the Vale, the mining company in Rio de Janeiro. They have here the peak shaving application. It's a 10 megawatt hour project. And you can see here at 6 p.m. at the start of the peak period, the batteries in white here are providing the excess power needed for the loads. The loads you can see here in the much darker orange, and the grid, the Enel, the utility company, is just seeing this line here around the 5 gigawatts. So you can see that the battery is floating since the loads here are floating, but for the grid, they are really flat. The time here next to 8 to 9 p.m., you can see that the load dropped, so the batteries even start charging for have some extra capacity to provide the peak shaving in the end here. You can see just a small power being provided here. So this is a case that is working inside a customer, but can easily be replicated for the distribution and transmissions company, as you can imagine this as a transformer, a power line, something that's being really overloaded at some times, and you can even operate the batteries the same way. Another great case that we have, this is another project for us in a shopping mall in Bahia. And at the same time, we are performing the load shift, the peak shaving that I just mentioned. We are fixing the demand here around 230K, and the batteries are providing the excess power. At the 6 p.m. here, you can see the power that the grid is seeing goes around zero here, because the batteries are providing all the power needed. It's like a peak shaving, but with a zero set point, so we call it load shifting. So it's an example of how batteries can make the multiple functions. We call it function stacking, and then the revenue stacking that we can have due to this. And at the same time, the battery energy management system can perform both functions, just depending on the time of day or any conditions, or even in forecasting, the solar forecasting, for example. Another quick example, this is not from a project that we have, but I'll go deeper into this later. This is a problem that the solar, especially the distributed generation, it's having. You can see here, it's the voltage level, this green line here. At the solar times that you can see here, the generation, this is just a small rooftop generator. You can see that the voltage rises a lot during this solar hours here. It's not caused by this specific system, but of course, a huge neighborhood with a lot of rooftop systems or even bigger systems can cause this kind of disturb. If we use the reactive power, we can consume some of this reactive power here. You can see now the voltage is still the green line, and the reactive power is the blue line here. We can, after a certain level of voltage, you can imagine around here, we can consume this reactive power and helping reducing this voltage, the total voltage of the grid. The opposite is also true. We can feed some reactive energy when the voltage is lower than it should be, and this way we can help with the stability of the grid in general. Most of you guys heard about the problem that we have a couple months ago about the voltage disturb that caused a huge power off in the distribution grids in Brazil, actually the transmission grids. So batteries could help a lot in this kind of this trouble and make the system much more robust. So that's why we can call the batteries the game changer for the ancillary services. Of course, they are mainly connected to renewable resources. That's why we are advertising this green thing about the batteries. But we don't need to install a giant battery that will solve all the problems of the Brazilian grid in all different levels. We can install then multiple batteries, and I mean a lot of really small batteries, but batteries that are seen as one big battery, or at least they have the possibility to understand the conditions and operate it to a common objective where we can solve all the problems, or at least help solving them with really small investments, and not actually made by the government or really big distribution or transmission or generating companies. It can be batteries that everyone here can have at home, connected to a photovoltaic rooftop generator, and if they have revenues related to the solutions that we can provide to the distribution grid, then we can use our own batteries to provide them. So why should we use this VPP style, the virtual power plant style deployment? First of all, we go straight to the root of the problem. We can solve the problem, for example, if a specific region is having trouble with excess of solar generation, we can install the battery there and solve the problems there. We need smaller spaces. We take about 10 square meters for 1 megawatt hour of storage capacity. So in some places, even especially in big cities, it's hard to have these huge systems installed inside the city. But if we have small, really small places, then we can make them work together as a big battery. The function flexibility, since we have a lot of different batteries, they can operate also in different operation modes. So we can have one battery making the load shifting, the peak shaving, the voltage control, everything at the same time. And of course, the modularity, we have a much more robust and resilient system, since if one just small battery fails, we have all the others operating. And that's why Micropower is deploying the first VPP in Brazil, the first VAS VPP, and the project is mainly focused on these ancillary services that we call all the sum of the service that we are performing, and is currently being deployed in Palmas, in Tocantins, in a really poor voltage quality neighborhood. It's really in the edge of the city, and the power lines there are not that good, and as they are a quite high income neighborhood, they have really high loads and a lot of penetration of solar resources. That's why we see in this kind of neighborhood that graph that I showed you before. And everything is gonna be remotely operated by the distribution company Energisa, along with all their energy resources. The solution is 6 fully integrated in metal container energy storage systems. They are quite small. They have 3 by 3 by 3 meters, so it's about the 10 square meters footprint that I showed, but we can put more capacity inside there. In this specific case, they are 1.4 megawatt hour in total, and sorry for the error there, but it's about 750 kilowatt power in total, summing all the system. And Micropower is doing all the design, the procurement, installation, and commissioning of the system. The main idea of the daily operation is really at the same that I showed you before, charging here at the solar peak times and making the load shifting or discharging them at the peak times. But all the other times of the day, we can make the voltage regulation since the battery is not operating, and as soon as we can use the power electronics to control the voltage level, we're not consuming or feeding the battery, we're not degrading it, and our asset is generating much more revenue since in no time of the day it's shut down. We can operate the 24/7 here. The design of the system is basically this. We have 4 sites. 2 of them are just batteries, and they are connected to the grid. And the other 2 have 2 batteries connected for more capacity and power, since they are associated to a 100 kW solar plant. So, of course, even we have the power connection, but all of them are grid connected to the central control. So this we have the visibility of everything, and we can operate them, as I mentioned before, as one huge system. These are some photos. You can see here the battery modules. These are around 5 kilowatt-hour modules, all then connected in series here in this part. We have the power electronics here, the power conversion system, and the container. You can see, for example, the air conditioning here, just to give you an idea. The system is currently being installed. Actually, it's already installed. They are commissioning. So I have some photos here of the system already in place. You can see the power plant over there, the 2 batteries that I mentioned. And currently our team is commissioning. They are making all the control objects and connecting it to the control center that we will operate. And soon we will have much more information about the system. It's scheduled to start operating by the end of this month. So hopefully in the next presentation, I can show you some results that we are acquiring, since we will have power quality measures all over this distribution line that serves these systems. Here, I'm not sure if the video will work. Yes, we were commissioning here. You can see that the solar generator is providing 49K, and the batteries are providing 12, so we summed about 61 kilowatt. So this was just the first test, but as soon as we have more, better results, we can show to you, and it's a really nice project that will be the first VPP operating here in Brazil. Thank you so much. If you have any questions.
Thank you, Vitor. Just for us to understand, is it Micropower? It's a private company. It was born inside the Federal University of Santa Catarina. Is it that?
No,
it's
no,
like a spin-off?
No. Actually, it's a American company that was founded there, but came to Brazil to just deploy the projects here.
I see. Now I see.
Not that much, because I'm here. I'm always close, but
do you have question? Just one question because of the time. Any questions? Yeah.
Do you see our company using Second Life batteries in your projects? Do you discuss this? Is that and how, in that case, how much would you be prepared to pay for a battery comparing to a brand new one?
Okay, that's a good question, because of course we have to give some destination for the Second Life batteries, but we see, at least in the past 3 or 4 years, a huge drop of the price of new batteries. We are talking about 35-40% decreasing of this kilowatt hour price and the dollar per kilowatt hour. And as we have some predictions, this cost will drop again by half in the next 5 or 6 years. So maybe it's kind of hard for the Second Life batteries to compete with this high descending curve, since these batteries were bought but much more money in the previous days. So at least they need to cost lower than the new batteries. So today we are talking about, for the whole turnkey system, about 3,000 reais per kilowatt hour. So the batteries the Second Life batteries should cost, I don't know, maybe 2,500 or something like this, because we have all the warranty issues, things that we still need to discuss.
Okay, Vitor, thank you so much one more time.
Thank you.
So we move to the next presentation will be from WEG company, Ricardo Rossa.
colocar um reloginho.
O laserzinho é esse aqui no meio, tá? Não é da ponta não, é o laserzinho.
Uhum.
Volta, Jonathan.
Ok, obrigado. Okay, can you hear me? It's okay? Thank you very much. Okay, thank you for the invitation to be here today. It's an honor to me to present our company and what we have done in the past few years in the energy storage market. We will talk a little bit about WEG, but a lot about applications of energy storage. We have plenty of applications deployed, and we would like to share with you what we have seen in these applications. Well, WEG, most of you knows WEG as a motor manufacturer company. In fact, we have here in Brazil the biggest motor manufacturer plant. So, but we are all around the world with plenty of factories and plus than 40,000 employees. And today we do more than motors. We do automation systems, we do drives, electronic drives, we do many things, including energy storage systems. So the numbers are here. Probably the presentation will be shared. I will not enter in details, but the message here is that WEG is more than a motor manufacturer. We produce coatings, we produce transformers, substations, every single equipment related to energy we produce, wind turbines and so on. It's important to say that here in Brazil, we have verticalized our operation, and today from a simple energy storage we produce since the start button that you press to turn on the system and up to the transformer that connects it to the high voltage system. So every single piece of energy storage is manufactured here in Brazil, developed and manufactured here in Brazil. And for this reason, I will focus on projects in Brazil to show what we have done here and what Brazil can do in energy storage, okay? Remembering a little bit of the concept of an energy storage system, the BESS or BESS. For WEG, we treat energy storage as power and energy under control. Basically because it is a junction of a battery or another kind of storage device, a power converter that mostly is a bidirectional converter that can turn DC to AC and DC and vice versa, and the AC to DC energy, and software, a lot of software that can control it. For this reason, we understand that you can do almost everything with the power and the energy that you can store in a system, basically limited by the physical size of the system, right? The main applications goes from electric mobility infrastructure. When you plug in a EV charger that is a high power EV charger in a normal gas station, you need more infrastructure to feed energy there. You can use an energy storage to do this work. Intermittent renewables, solar and energy. We are in Brazil at this moment discussing about the inclusion of this technology in the capacity reserve auctions, where we are suggesting to include renewables with batteries associated with BESS to have to make these power sources dispatchable. Okay, you can have firm energy exactly as you have with thermal power plants. Microgrids, as Victor showed us, is possible to do VPPs and microgrids. We have done some here in Brazil. Ancillary services like energy shifting, peak shaving, frequency regulation, and so on. I will show some here, and much more. The customers are various. You see energy storage since the house to the transmission systems. You will have applications for all how can I say, all parts of the electric sector. So the energy storage for us is something like a Swiss knife. It can perform many applications, including at the same time. I will show here. Okay, there are two topologies that we work with energy storage. The basic one is that the common AC coupling energy storage, where you have the grid feeding energy to the load, the PV inverter or other power sources connected to the AC. It can be diesel, PV, wind, farms, hydrogen, green hydrogen, and so on. And the batteries and the bidirectional inverters will help this point of connection with the energy. How can I say? Storing and deploying energy at this point in parallel to the grid. But there are an inconvenience here, that is the islanding system, that when you need to disconnect the grid and have it working alone, there is a switching time here for electromechanical switches that can have a small interruption on the feeding energy to the load. So in the UPS mode, we use two converters, one working as a rectifier and another working as an inverter in the batteries, but in series with the load, right? Between the grid and the load. The load have energy provided by the inverter directly, and the rectifier gets the energy from the grid and put it in the batteries. If the grid fails, the rectifier stops and the battery supplies energy just to inverter, exactly as an UPS, a huge UPS. This is interesting because we don't have the switching time that you have in this kind of topology. But the inconvenience here, the drawback, is that you have two inverters and the complexity here is bigger than the other one. So we suggest this only for critical case, right? Critical power applications. There are many application modes, operating modes. Victor gave us many samples, but I can tell you that we can do power factor regulation, peak shaving, voltage and frequency regulation, spinning reserve, load leveling, time shifting, power stabilization, energy management, and black start. Okay, you can start, for example, a power plant using batteries instead of other technologies. Also, our friend also spoke a few minutes ago. We have the two stacks. One stack of costs that is related to the battery costs, the power electronics, the balance of plant, O&M, and the commissioning. That is a cost that must be considered. And we have the revenue stack. The revenue stack is based on that applications, when you can make more than one application in parallel or in series. And then you have revenue for each one. And then if you have, for example, an investment deferral for a substation, if you have time shifting, for example, if you can buy cheap energy and sell it when the price is higher, spinning or reserve, that exactly we are talking about the capacity reserve, frequency regulation. And then when you put this in the stack, and this is bigger than the costs, you have feasibility, right? Typical applications, Victor also already mentioned it, but energy shifting, you can charge the batteries when the power consumption is low, and then use it, for example, in the peak time, doing where the energy is expensive, or even taking advantage of the solar excess of energy, using this in another moment. It is useful for example, when you have curtailment and constrained off in power plant, in solar and wind power plants. Peak shaving, where you can reduce the the contracted demand of the utility, so you can charge the batteries when you have excess, and then discharge it when you don't have, for a generator plant, or vice versa, when you have consumption exceeding your demand, you can just use batteries to supply the energy, right? And for renewables, you can have it power smoothing, for example, to avoid peaks and other behavior for the generation that you have on intermittent power sources. Here, I would like to share with you a real graph of an application that does exactly what we have, that is related to the stack value. Here we are in the United States, in Vermont, doing frequency regulation. At this site, you will see two curves here. The blue one is related to the power injected or stored from the system, right, or absorbed. And the orange line is the battery state of charge. It means that the battery in this application is still around 40 and 50%, right? In this case, the system operator sends a command every 4 seconds for the energy storage. You will not have other power source that can do it as fast as a BESS. So each second along a day, each 4 seconds you have a command. So you can inject 2,000 kilowatts, absorb 2,000 kilowatts, and goes every day. This is an ancillary services named frequency regulation, and there are plenty of how can I say, services like this, like fast frequency regulation and others. But you do it and you receive some money for that. So some investors do buy energy storage just to do this. But if you can, for example, put another application in the stack, in this case, in the determined hour of the day, you charge the batteries and you see that the energy absorbed for an hour, and then you have 3 hours injecting this power, 1 megawatt hour for 3 hours. So you have here a peak shaving between two sets of frequency regulation. Then you come doing something, then you change your mode, and then change again. In this case specifically, the utility avoided a penalty of as $100,000 just for this event. So this is something that you don't see every day, because it's a real application where you have frequency regulation. As I told you, we produce everything here in Brazil, but basically this slide is to show you that everything starts from a cell, a battery cell. The battery cell is assembled in modules and racks, and then you can have multiple applications, indoor, outdoor, or even a containerized version of it. But the biggest application for us here in Brazil and worldwide is to do it electrical mobility pack, where you have plenty of batteries. You have also the liquid cooling systems and the firefighting systems integrated, and then you can use in vehicles like cars, trucks, and others. So it's a trend, and now we are talking in the academy, so it's good to talk about trends, to have the cell to pack directly, so you avoid to pass modules, racks, and so on. Cell to pack, and you have these packs used on the energy storage. In the near past, we used racks, and now we use electrical mobility packs. I will show you more trends on this in the next slides. Okay, basically we talked about the block diagram. We talked about applications, but physically how it seems. Victor showed us a video and some pictures, but it's important to say that energy storage have many forms of presentation, many assembly types. You can assemble, for example, in this case, everything in a single container, wherein you have the transformer that connects to the medium voltage. You can have the electric boards, the DC board, the AC board. You can have the power converter system that we name it PCS in best, how can I say, vocabulary, and then the batteries. In this case, we are showing here batteries, air-cooled batteries, cooled by an HVAC system. But you see that the most common nowadays is the liquid cooling systems due to many factors, right? But this one is a completely integrated system, so we name it all-in-one systems, including transformer. But it can have medium voltage switch gears or others, since you can do it inside a containerized version. And the most common for big systems is something like this. You have battery containers that we name it DC blocks. The DC blocks can have a huge amount of cells or racks, or even the packs that I showed you. And this one is the batteries, and then you have transformers, the inverters. These white boxes are inverters, so you have a container, and then you have here a block. You have a DC block, the PCS, the power converter, and then the transformer. This is named a block, and then you have, then you can multiply it as many times as you want, since you size the wiring and so on, the connections. But you can expand this and multiply it by hundreds, and have, for example, gigawatt systems. Okay. In this case, we have 10 megawatt hour systems that is deployed by WEG in the United States using BYD containers and so on, because there, in that time we didn't have the certifications to sell our equipment in the United States. That now is in progress. But you will see here the second way to see the physical aspect of an energy storage, an utility scale energy storage, right? Talking about trends, another trend is to have the equipment mounted above a skid. A skid is a metal basis where you can have, for example, the modular PCS, the transformer, and the switch gears, the medium voltage switch gears, all integrated. Why? Because this is more practical and more cheaper than making too many connections in the field. At WEG, we say that in the house it costs 1, in the field costs 10. So it's very easier to do it in the house, in the factory, and send it ready to the field. In this case, we will just connect here the plus and minus cables, simplifying obviously, and then the ground and the communications, and the other side you have R and T phases, and then you can run your energy storage happily. Another trend is the density of the racks and the batteries. Every year, the battery cells manufacturers publish newer versions of their products. We are talking about something around 10 or 15% of increase every year. If you try to buy a battery today and buy the same battery next year, you will find the same form factor with increased capacity. And this is what we have today. You will see that we have, for example, BYD, CATL, just releasing some batteries based on cells. You can imagine 587 amperes hour. In a simple container of 20 feet, we are achieving 6.2, 6.7. We have yesterday I saw a recent launching of 6.9 in a single 20 feet containers. So you can mount blocks with 2 or 4 containers side by side, because the maintenance can be done from one side. You can imagine 7 per 24 megawatts hour in a single block. It's a huge amount of power. Okay, and you will see another manufacturer that is moving on based on cells of the half of it. If you see the containers in the last year, you saw here, for example, we have 2 point something, 2 let me check, 2 megawatt hour per container, something like this. At this moment, we are talking about 6. It's the triple. So this is a trend to increase the power in the containers, right? Just talking about the components of an energy storage, this is, as an example, the WEG best product portfolio. We start from the smallest version of our inverter, starting on 30 kilowatts, up to 3.6 megawatts in a block that can be mounted in a skid with transformers, and then the medium voltage stuff. And then lithium batteries that can be done in racks or outdoor racks. This is a common product. I will talk about it in a few minutes, because CATL is using this as NR1. The name is NR1. And up to 3 megawatt per container in a single all-in-one system, right? Or 40 feet. But you will see other integrated solutions for commercial and industrial applications, utility, and mobile application. I will show our track record, and it will be easier to see. Well, as I told you, there is plenty of applications for energy storage. Here we can sample of it. We are talking about connecting energy storage to a wind farm, connecting energy storage to do ancillary services. Rocket launch base here in Brazil of Alcântara has a microgrid made by WEG also that replaced the diesel generators to make the rocket launch. We are talking about hydrogen power plants. If you need, for example, green hydrogen, you need green energy to produce green hydrogen, right? And probably this energy comes from an intermittent power supply. The batteries helps to stabilize this one and deliver to the electrolyzer energy, stabilized energy to produce this material, this green energy to produce green hydrogen. And mobile applications. I will probably have a picture. Yes, I have a picture of each application. When we're talking about e-mobility infrastructure, as I told you, if you install something like this this is a Select project. Select is here. Okay, this is a project we have done with Select in 2016 or 2017. And then we put an energy storage, one of our first energy storage to support this application. This is the green hydrogen power plant. You can see here, but behind this system, you have a green hydrogen power plant. The first one here in Brazil is a 600 kilowatt hour in Itumbiara, a project made for Furnas that is working there for R&D purpose. Here is the photovoltaic UFSC Second Life Systems is a kind of a lab where we are comparing the new batteries, new Samsung batteries with Nissan batteries, used or Second Life batteries, right? You probably will see tomorrow in the visit or in the afternoon in the visit to Photovoltaica. Is there, it's working. This is another Second Life application where we have BMW vehicles being fed by BMW Second Life batteries powered by a solar carport. So we have energy coming from the sun, storing in the used batteries, and then being deployed to the cars, all green. So there is no grid on this. This is mounted in Araquari in the BMW facilities, so it's working. Here's the other project in Tubarão, Santa Catarina, where we have a wind farm working with solar and the energy storage systems for R&D purposes also. Here is to exchange diesel generator. As you can see, we have many applications. Energy storage is a very flexible and very, how can I say, flexible and useful system that can replace energy, that can help other systems to work, and so on. Here's another project in Belo Horizonte for Federal University of Minas Gerais for comparison technology purpose. They have lithium-ion and lead-acid batteries to side by side to be compared. We have projects on islands, for example, Fernando de Noronha. We have solar plus storage installed there, to also as an R&D, but now they will have a big project to try to decarbonize the island. The rocket launch base, as I mentioned, we had there plenty of diesel generators. Now we have an energy storage, a 1 megawatts energy storage, supporting the rocket launches. As well, we have projects with Copel to connect it to a substation, a distribution substations to help to integrate solar and make the backup energy, for example. All these projects are available for discussions if you want after this meeting or something. You will have my contact. We can give some details, not all because some of them are private, but you will see what we have. Here we have another island with a small microgrid. Now we have another trend that is the long duration energy storage. In Curitiba, we have a plant with lithium-ion side by side with flow batteries. I'm just finishing. And now we have the mobile applications, a big one with 1 megawatt hour. Today we can do up to 3 megawatt hour inside a truck. So this one was sold to Copel. This is a mobile version to be connected to the medium voltage also. So just to help on turning off substations and so on to increase the duration, to decrease the duration and the frequency of the cuts, the power cuts. Here we have some United States projects just to talk about the applications also. Frequency regulation and peak shaving, exactly that project you saw at the graph. So you have both functions performed here. Another one, now it's very easy to see how BESS can be formed. Batteries, power converters, transformers, and then the grid, the medium voltage, side by side. Now here we have underground wiring. Another project that is, how can I say, didactic. You can see batteries inside a container, converters, transformers, and then the grid, doing frequency regulation as well. Another case where we have back-to-back, an example of back-to-back containers, because the batteries are, the maintenance is only from one side. Imagine that you can put 4 containers like this. If you have 6, you have 24 megawatt hour inside a 4 container set of this, the power converters, transformers, medium voltage, and so on. It's just finishing. Frequency regulation and ancillary services is another one that I showed. And here we have other projects here in Brazil. The biggest projects are here in Brazil we have is a 60 megawatt hour from ISA-CETEP in Registro, 60 megawatt hour and 30 megawatts system in a substation, in a transmission substation from the utility ISA. This is working, this is avoiding energy faults in São Paulo, São Paulo state. This is exactly the project that Victor mentioned. This is one from micropower using Tesla batteries. This is the second, I think that this is the second biggest in Brazil. The first one is this in transmission. The second one is this from 10 megawatts hour. And we are talking about big projects, but we also have the smaller projects that produced by another competitors that can be deployed, that are deployed in the Amazonas and off-grid systems that gave life for people that don't have access to the national integrated systems. Okay, just a final message. When you lack machines, you can buy them. If you don't have money, you can borrow it. But if you cannot buy or borrow people, and people who are motivated by an idea are the basis of the success. This is a phrase of Egon, one of WEG's founder. I just want to be grateful for being here. Thank you for the audience, and this is what I have. Thank you very much.
Thank you, Ricardo. It was very impressive numbers and a huge portfolio. Thank God that I bought some shares of WEG 2 years ago.
Oh, thank you very much.
Not too much.
Okay.
Question, just one question at least. You have something? Yeah.
Thanks a lot for interesting presentation, and it was a pleasure for me seeing how it developed, because about 10 years ago I visited WEG, your company there, and there was early beginning of the battery business there, so it's nice what happened there. And you're really making the cells yourself here in Brazil?
No, we produce, the cells are made in China, but with a project made by WEG. We project our cells and someone produced by to our cells.
Oh, good.
Okay, so we start from the cell. We buy the cell here in Brazil. It comes from there. It's a matter of demand. We don't have demand to have a gigafactory, for example. So we contract someone to make it for us, and then they manufacture there. We import it here in Brazil. We don't have it. There's no cell manufacturing in Brazil, and so we just integrate it on a system. But we do the BMS, the EMS, all the stuff around the batteries. We do it.
Yeah, that's nice.
Okay.
Yeah, thanks a lot.
Thank you very much.
Ricardo,
Okay.
thank you again.
Thank you very much. Have a nice day.
So let's move to the presentation for some opportunities from DWIH from Márcio. Thank you.
Okay.
Lê esse segundo, tá? Não é o primeiro, não, o segundo.
Eu uso mais só para passar. Obrigado. So good morning or good afternoon. So I'm very happy to be here and supporting the symposium, as I said yesterday, and I have learned since yesterday a lot with you, with your presentations. And now I will present our DWH, as we spell in German the name of our German Center for Research and Innovation. I will present you also some German funding programs. And that is very interesting, very good that we have some representatives of companies here, because the last slides are for industrial research on international level. Yes, I will start my presentation. So the WH, we are a network of 6 units worldwide, and all of the network is under the umbrella of the DED, the German Academic Exchange Service, the largest organization worldwide for academic exchange. Each DWH has its own supporters. They are called supporters. And we are very proud that we have in São Paulo, in Brazil, the highest number of supporters linked to one DWH. So that are many universities, non-university research associations, funding organizations, and others. These are that are linked to us in São Paulo. You see three agencies. So the first supporters are these organizations that have own representatives in Brazil. Okay, so you have agencies, Fraunhofer, 3-4 universities, and others. And associated supporters are the organizations that are linked to the WH, but they don't have own representatives in Brazil. They can apply for subvention for events, as I will present later, and so on. You can see it's not what I did here. Okay. Onde que é mesmo o pointer? Aqui tem botão?
Tem botão aí.
Okay. So you can see here the Technische Hochschule Ingolstadt, so one of our organizations here, and the University Alliance Ruhr, so the University of Duisburg-Essen. We have 2 colleagues here as well in this meeting. So we have some representations of the states of Bavaria and Baden-Württemberg, and other organizations like IF, that is for industrial research. And our objectives are to promote knowledge exchange, so scientific knowledge, but also knowledge about the scientific and innovation ecosystem of the countries, and to promote them. So promote networking between scientists, researchers, innovators, multipliers, and decision makers, and so on. And we offer advice about study, research, innovate, and so on. And we do marketing to increase the visibility of Germany as land of ideas, but also from Brazil in Germany. We do marketing for Brazil in Germany, so that the German researchers can be interested in Brazil as well. So our activities are on the area of scientific cooperation and the interface science business. In the last years, we increased our activities with startups, research-based startups, and on the area of study, research, and innovate in or with Germany. This is the common area of the DED. This we have each year main topic. This year we have two. So the main topic of the network is artificial intelligence in a very comprehensive approach. But in Brazil, we have also the 200 years jubilee of the German immigration to Brazil. Here are some highlights this year. This week, I'm here, and our colleagues are in Rio. They had yesterday the first postdoc workshop about postdoc in Germany. It's a very consolidated initiative. We have it each year. And on Saturday, it will happen in São Paulo as well. I think you know this one. So we are very happy to be supporting this initiative. And the other topic, so we can find us as well each year on the annual meeting of the SPPC, the Brazilian Society for the Advancement of Science. It's a very interesting and large event, but more on the area of politics, science, politics, and innovation politics, and higher education politics, and so on. We will have in July an event as well to artificial intelligence. And here are the list of the other projects of us. For example, here with Fraunhofer, one EdTech hackathon, for example, and so on. Yes, and the end of the year, we will have a Young Innovators Week for young innovators from Germany and Brazil. And now the funding programs. So the VH itself is no funding agency, but we are in a funding agency, the DAD, and we have money. We are full funded by the German government, by the Foreign Office, and we have money to finance events. But we can only finance events from our supporters, like TH Ingolstadt and University Duisburg-Essen. Okay, so so if you have cooperation with this organization with other supporters of the VH, you can talk to them and ask them to prepare an application for a workshop like this or a symposium or other events. So the full supporters can apply for 8,000 euro, the associated for 5,000 euro. Okay, this year our selection is concluded, but next year, so the first call for next year should be in August or September, maybe. So we have a lot of possibilities of formats of events that we can support, but also other projects in the area of scientific communication. So, and now the funding programs that are really for research or for mobility. The DAD so has a winter course for that ones that are students, master students, and they are learning German, so they can apply for this program. Then we have master, so fellowships for master. I will present. I have a slide about EPOS, but I want to talk about the Helmut Schmidt program. This is a program not is for public policies and good governance. So you are more of the area of technology, but if you are interested for capacitation about management of, for example, energy transition and so on, and the public policies and so on, we can apply. You can find there an option as well. The EPOS program is a program related to sustainable development. Most of them are master courses, and you will find here under engineering and related disciplines some offers in this area of energy, for example. This is this is a program that's not for academic people. So the colleagues from the companies maybe or for public administration should be more interesting because you need 2 years of professional experience after your study, after the graduation. Okay. Then that is very interesting for you. So this is a program that is with money from the European Commission, the area fellowships in the area of green hydrogen. That is so Brazilian students can apply, or graduates can apply for a master course or a PhD program in Germany on the area of green hydrogen, and not only in the engineering area and so on, all areas, also in management or in politics and so on, can apply for this program. And also from Germany, graduates from Germany can apply for a study or a research stay in Brazil as well. There are other components in this program. I think for postdocs is also in the program. So I know that they have as well a platform with working groups on green hydrogen to promote networking, online networking between not only researchers but also representatives from private sector, from companies, from governments, and so on. This is so like a think tank, a network. And as I know, they are preparing a call as well for a tour in Germany this year. So people from Brazil can apply for this tour as well. So this is the main program of the AD in Brazil for PhD in Germany. And you have here many possibilities. So a full program or co-tutel, so with double degree at the end, or 1 year grant, so sandwich, as we say in Portuguese, in Brazil, sandwich fellowships, okay? And there is another program from DAD for short stays during the PhD. If you have a fellowship or scholarship by CAPES or FAPESC, you can apply to have additional fellowship from DAD to stay from 2 to 6 months in Germany. So DAD fund as well the mobility of researchers, scientists that are professors or researchers in research institutions, 1 to 3 months in both directions, from Brazil to Germany, but also from Germany to Brazil. And there is a research days for the alumni as well. So if you are alumni, so you have many offers to come back to Germany. The professors can organize as well groups of 10 to 15 students to visit Germany, not for tourism, but visit research institutions, universities, and so on. So it's a very interesting program. It's not very known in Brazil, but some professors know it and use them. Yes, and this now is an institutional program. Ricardo has already mentioned it in his presentation. ProBrau is a cooperation with CAPES. So the research groups from both countries can join and develop a research project. But I think most the money of this funding is for mobility. It's not for the research itself. And the has now also PROPASP and PROPAR. It's like PROBRAU, but with the states of São Paulo and Paraná. Yes, that is other possibilities. So, so Brazilian professors, universities can invite German professors for a stay in Brazil as visiting professors. Yes. And now the next agency, the DFG. DFG is the German Research Foundation, is the largest funding agency for science in Germany, but more concentrated on basic research. So DFG has cooperation with FAPESP, also with FAPEMIC and FAPEAG, no, but here is more, it works better with FAPESP. We need to recognize it. And so they have programs for initiation of international cooperation. They have program for bilateral collaborative projects. And in Brazil, that was only one case of international research training groups. This is a very different levels of funding here. And they are applying or promoting now this option as well. The Walter Benjamin program. It's a fellowship in Germany with a position there. Yes, for 2 years. It's like a postdoc option. And this is other position for principal investigation. So if you get this fellowship, you will have money to organize your own research group, and we will have fund for many other costs for your project. So Alexander von Humboldt Foundation, this is also only fellowship, individual fellowships. It's in cooperation with CAPES. They offer fellowships for postdoctoral and for experienced researchers, okay? And here is more important the people, the researchers, so the curriculum of the researcher is more important than the project itself. Yes, the next, the currently call and at end of May. And there is a program, funding program for about climate protection. So the candidates need to be graduated and they can stay in Germany, not only in universities or research organizations. They can go to companies, to public administration, to NGOs. It's a fellowship for 12 to 24 months, not necessarily with a title at the end, but can link to a master degree, for example, as well. And this is but more focused on the market, so that the fellows will be multiplier and experts on the topic. And I think maybe can link to your topic here of energy. So BILAT is an organization of Bavaria. Is the Bavaria Higher Education Center, or Bavarian Center for Latin America. Okay, they promote the cooperation of the institutions of Bavaria with Latin America, and the executive director is a Brazilian woman. So and the work is very well, working very well. So they have this call to start cooperations Okay. This order is with FAPESP. I think there is no one from Sao Paulo here. And this is a very interesting because I don't know other funding program in Germany or for Germany. So students from the graduation, undergraduate students or master students, they can apply for a stay to 5 months in Bavaria to do a research to conclude the TCC. So at the end of the course or the dissertation of mestrado, okay? And this is very, very unique, I would say, in the constellation that we have of funding programs. And in the framework of Amazon Plus 10 initiative of FAPESP, of CONFAP, CNPq, and so on, BILAT is the one's organization in Germany that is offering support as well, so good for the colleagues from Ingolstadt and other cities. So, the researchers from Bavaria can participate in so-called scientific expeditions in Amazon. Okay, and they, I don't know if Alessandro is aware. So it's obligatory to have researchers from the region as well in all projects. Okay. I think your topic fits probably here in this description. And then closing the presentation, the program for industrial research. So IEF is our organization for industrial research on the small and middle enterprises in Germany. And they have money from the Ministry for Economics, named Erasmi. And in this network, in this program, so companies from both countries, from Germany and other countries, for example, Brazil, they can present a R&D project and apply for funding. The Brazilian side needs to have the funding from Brazilian side. Okay, so Embrapa is partner of IEF, and I think Senai as well, but it's not here. So maybe, but they are open with, so if you find support, so they are accepting it. Okay, and here's contact of Felix, very open to discuss all of them. So Fraunhofer has many projects that are financed by Erasmi. Okay, I think was, so here are our channels, our media. So I recommend you to sign our newsletter because what we presented in these PowerPoints are the regularly programs, but every year we have extraordinary programs, funding programs. And so the best way to know them is through by our newsletter. So, and LinkedIn is in the moment our main platform as well on the social media. And here you have my contacts as well. Thank you very much.
Thank you, Marcio. Do you have questions? Yeah.
Thank you, Marcio, for this very comprehensive overview of the funding opportunities. Would it be possible for us to receive this presentation?
That's no problem. So you have the file. Okay. Maybe someone can convert to PDF and distribute. No problem.
Okay, thank you.
It's not a question, it's just a comment on, I was myself von Humboldt Stiftung postdoc fellow in the Fraunhofer Institute 30 years ago. and the von Humboldt Stiftung has for developing countries a scientific equipment donation program. And this is how we got our first grid-connected PV system that I showed earlier today. This was a donation from the von Humboldt Foundation, fully monitored system. Started my career here in Brazil. Not only sponsored my postdoc there, but was also the way we started this lab that you will see this afternoon was started with that grant.
Yes, as I know, this funding continues. And the idea as well, the idea, I think they don't offer equipments, but books. So the alumni can books or the books for research.
Thank you, Márcio, one more time.
Thank you.
Let's do the final presentation. You'll be with Rodrigo from Federal University of Santa Catarina. And we will learn a bit more about EMBRA-P. It was told here about some funding.
Like that, so.
Tá perdida, mas ela não é o último botão, é uma intermediária, tá meio apagada aqui, tá?
Tá. Ah, ok. E para avançar, tá. Ok. Ok. Good morning to everyone. For me, at least, it's good morning. It's still good morning. So I will try to go faster as possible to present our Unity, our EMBRA-P Unity here in Florianópolis. Actually, I have 5 EMBRA-P Unity in Florianópolis. One of them is our Unity. You spend a lot of time to find a word that works good in Portuguese and in English. So move in English, move in Portuguese. This is the same sense. Well, I'm gonna talk about the EMBRA-P, how it works. It's more or less aligned with the predecessor presentation. And what is EMBRA-P? EMBRA-P is an acronym that means Brazilian Company for Industrial Research and Innovation. It was created in 2013, and EMBRA-P it's a network of research centers. I'm going to talk a little bit after. And the mission is to enhance innovation capability of Brazilian companies. The proposal here is to create in a more intentional relation between companies and universities. They provide the financial resource, and we have a network of 96. The last number that I have is 96 units, 96 research centers around Brazil. Those centers are very specialized. For instance, we have centers based on artificial intelligence, on laser technologies, on manufacturing process, on IoT, and so on. Our center that we call Unity is specialized in mobility. So you are a partner. You propose to be a partner of mobility industry in Brazil. To make a contract inside the EMBRA-P model, you have some lines of action. For instance, in MOVE, you have 3 different lines. The first one focuses on vehicles and equipments. So we are dealing especially in parts, in vehicle parts, or the whole vehicle. It can be a partner to develop some technologies here. I'm going to talk a little bit after. The second line that we work is device and equipment energy conversion. Nowadays, we are talking about hybridization, biofuels, so we have competence to work as a research partner, scientific research partner in this area. And the third line, more addressed to process. The first two is more addressed to products, and the third is more addressed to process, manufacturing process, any kind of improvement of manufacturing system or materials, development of new materials, new alloys. You have competence, you have a crew to work on this. As I said before, you can act from the two different points of view. The first one is product development, so you can help to create a new product. You can also work on improvement of the existing product and to aggregate new technologies. From the side of the process, they are very similar. A new project creation, implementation of a new technology. For instance, if some enterprise have low profit based on his process, on the manufacturing process, you can help to improve this. Actually, we have two projects nowadays. We have two projects based on this, on the implementation of new technologies on the process, on the manufacturing process. How you can find the funds in IMBRP? The movie Unity works on 4 different lines. The first one is we call the standard IMBRP financial mode, where IMBRP pays 1/3 of the project, and the 2/3 are arranged between partners and Unity. I say partners because you can make a project with one enterprise or one company or more. So this you have to arrange the budget to arrive on these values. IMBRP usually pays at least 10% of the project, and same as for the partner of the project. Both of them, IMBRP and the companies, enter with the financial counterpart, and the Unity can supply economical counterpart to make the project. The second way to have a movie as a partner is inside the SEBRAE IMBRP project, financial project. SEBRAE is an organization that focus on micro and small enterprise in Brazil. Here we have also an individual entrepreneur. It's a very particular way. And in this project inside SEBRAE IMBRP, you can work with micro and small enterprise, individual entrepreneur, and startup. Here again, we can hire just the small enterprise, for instance, or more than one small enterprise, or small enterprise and a medium or large company. For instance, if a large company has a supplier that is a small enterprise, you can make a project with both of the companies. There are some rules, there's some restrictions to be in this kind of on this kind of financial, because it's very good. SEBRAE pays 70% of the bill, so it's very attractive. And there are some rules that restricts a little bit the project. For instance, the small enterprise, the startup, only can hire 2 projects per year. The medium, large company and the startup in medium must be of the different groups. they cannot share employees or collaborators between them. In this case, if you have a large or medium enterprise in this project, they must pay at least 15%. There is no limit. They also can pay all the part of the enterprise, and in different from the standard MRP model, here the MRP can pay at up to 15% of the project budget. The third line here you used to call as a parallel actuation because we are accredited to work with these three lines, and they are not they don't need to be proposed for from mobility enterprise, mobility company. The first one is national defense. So when you talk about security or national or defense, you can be a partner in this domain. Digital transformation, that means Industry 4.0, IoT. You have this capability to work on this. And advanced materials, in this area we are very strong, advanced materials. So that means the development of new alloys, development of new materials. You have very good facilities here in UFSC that work on this. And the last one is the international cooperation, as was presented before. For instance, the Erasmus. It can be a partner from the Brazilian side, and this kind of cooperation, each part pays its costs. So Brazilian side pays the Brazilian costs, and abroad side pays the abroad costs. For instance, if you have a big company that have a headquarters abroad Brazil, and they have a branch here in Brazil, for instance, you can use both companies to make a project, a research project, and from the Brazilian side, you can find some funds from Embrapa. Actually, you can use co-funding projects. You can put money from another source, and you have also the money from the Brazilian enterprise, Brazilian companies. And same of the abroad, we have to find an innovation agency over there, and international enterprise, and it's possible also to use co-funding projects. Just to finish, I bring to you one of the projects that are running nowadays here in MOVE. Actually, we have 11 projects running at this moment, and about 12 million reais of budget. That means 2.1 million euros of project. And this project is a small part of diesel engine that you can use as a generator. It's a sintered material and manufacturing process applied to tapped pin for diesel injection. So you have a lot of NDAs. Have assigned a lot of NDAs, so I can show this for you. But when I make a project inside the Embrapa, you have to define some micro activities. The micro activities are proposed in this project are these 4. So we started production of a prototype, and you can make the prototype here in your facilities. The second one was laboratory evaluation. Actually, we are here in this project, in this micro activity too. Then you can use a specialized bench for evaluating the prototypes. And the final part is pilot scale of production. You have an installation here at the university that can create some pilot production parts and from small size. What is innovation here? The innovation is that this part of this component of this part usually is machined by steel, and here we are using the powder metallurgy. So you can add some self-lubricating properties in this material. You can add the steel and another chemical elements that can make that can reduce the friction coefficient, and you can, in the first evaluation, they find very low values of friction in this component. Reducing the friction, you can increase the life of this component, so we reduce also the wear of this component. Adding some components, we can also increase the strength of this part of this material. The powder metallurgy, it's considered an eco-friendly action, eco-friendly manufacturing process, and as a solution, also can have a large scale production for this kind, and obviously reducing the wear. You can have a cost reduction for maintenance of this part, and also for the production of this part. And this is that I propose to present today. I try to not delay so much the lunch of everyone. So I give it.
Thank you, Rodrigo.
Thank
you
you
so much for the presentation. Do you have questions? Yep.
We spoke last year about having joint project with our German colleagues here, and at that time, one of the difficulties was how do we transfer money, how do we pay our German colleagues, our German cooperation partners. Has that changed? And in all of your projects, have you had an experience where you have already exercised this idea of how do we pay our German partners if the German part is not coming with their own funding?
As I told before, the rules didn't change, so they have to pay the people, the staff from outside.
Okay, but if there is a German company that has a subsidiary here in Brazil, then how that arrangement will work? Let's say we have somebody from a German company, but they have a representative here. Would that make open a possibility?
Yeah. Well, it's a good question. Actually, if this person comes to Brazil to work in that company, he can justify that you're working on Brazil.
As long as they're working here.
Yeah, probably, but I'm not sure. But I think it's possible.
Okay. Thank you.
Yeah, welcome.
Any more questions? Not? Thank you so much.
Okay, thank you. Thank you for the audience.
So we finished this part of the workshop today. We have through the afternoon visiting in the north of the island, the facilities of the photovoltaic. And thank you so much.
Vou levar para casa o microfone.